Look up at the stars tonight, and here's the astonishing truth. What you see is just a fraction of reality. In fact, 95% of the universe is invisible to us, hidden in plain sight. It's a cosmic mystery that defies everything we think we know, filled with forces and phenomena so strange they sound like science fiction. But this isn't fiction. This is the frontier of human discovery, where the rules of physics twist and the universe reveals its deepest secrets. Today, we're embarking on a journey to explore 50 of the most mind-bending insights into these hidden realms, from the ghostly grip of dark matter to the terrifying wanderings of rogue black holes. Each one challenges our understanding, rewrites the textbooks, and leaves us staring at the night sky with more questions than answers. Think about this for a moment. Everything we've ever touched, seen, or measured, every star, every planet, every speck of dust, makes up just 5% of the cosmos. The rest is a shadowy enigma, a puzzle scientists are still scrambling to solve. What lurks in that unseen darkness? How does it shape the universe around us? And what does it mean for our place in the grand scheme of things? These aren't just abstract questions, they're clues to the very fabric of reality, waiting to be uncovered. So if you've ever felt that tug of curiosity when you gaze at the stars, if you've ever wondered what lies beyond the edge of our understanding, this journey is for you. We'll dive into cosmic anomalies that bend space and time, explore forces that could rewrite the laws of nature, and uncover mysteries that have baffled the brightest minds for decades. By the time we're done, the universe won't just seem bigger, it'll feel stranger, more alive, and more thrilling than you ever imagined, ready to step into the unknown. Let's begin. Picture a universe where the stars and galaxies you see are like tiny islands floating on an invisible ocean. That ocean is dark matter, an unseen force so powerful it holds entire galaxies together with its gravitational pull, yet remains completely invisible to our eyes and telescopes. Here's what makes it so baffling. When astronomers calculate the mass of a galaxy based on the visible stars and gas, the numbers don't add up. There's far more gravity at work than what we can see. Without dark matter's hidden scaffolding, galaxies would spin themselves apart, flinging stars into the void. But how do we know dark matter exists if we can't see it? Imagine watching leaves swirl in the wind. You can't see the air, but you know it's there because of how it moves everything around it. That's exactly how scientists detect dark matter. They observe its ghostly fingerprints in the way galaxies rotate too fast, in how light bends around invisible masses, even in the cosmic web that shapes the universe's large-scale structure. Yet after decades of searching, no one has directly captured a single particle of it. The leading theory suggests dark matter could be made of weakly interacting massive particles that barely interact with normal matter except through gravity. But experiments deep underground, where scientists hunt for these elusive particles, keep coming up empty. This has sparked wilder ideas. Maybe dark matter isn't particles at all, but primordial black holes left over from the Big Bang. Or perhaps our equations for gravity are simply wrong, and we're chasing shadows that don't exist. What's at stake isn't just scientific curiosity, it's the foundation of physics itself. If dark matter is real but unseen, it means the universe operates by rules we're only beginning to grasp. If it's an illusion, then Einstein's theory of gravity, which has guided us for a century, might need a radical rewrite. Every discovery or dead end brings us closer to answering one of cosmology's biggest questions: what truly holds the universe together? Until then, dark matter remains the universe's most tantalizing secret, a reminder that reality is far stranger than it appears. Just when you thought dark matter was mysterious enough, the universe throws us an even bigger curveball of dark energy. While dark matter pulls the cosmos together with its invisible grip, dark energy does the opposite. It's pushing the universe apart, accelerating its expansion in a way that defies all logic. Imagine blowing up a balloon with dots on its surface, except instead of the dots moving apart at a steady pace, they suddenly start racing away faster and faster. That's exactly what's happening to our universe, and dark energy is the force behind it. Here's what makes this so mind-blowing. Dark energy makes up a staggering 68% of the universe. That's more than twice the amount of dark matter and over 13 times the amount of ordinary matter combined. Yet we have no idea what it actually is. Einstein once proposed a similar concept called the cosmological constant, a sort of energy inherent to space itself, but even he dismissed it as his biggest blunder. Turns out he might have been onto something. So how do we know dark energy exists? In the late 1990s, astronomers studying distant supernova made a shocking discovery. These exploding stars, which should have been moving away at a predictable rate due to the universe's expansion, were actually accelerating. It was like throwing a ball in the air, only to watch it shoot away faster instead of falling back down. This observation flipped cosmology on its head, earning the researchers a Nobel Prize and forcing scientists to confront an unsettling truth. Something invisible is stretching the fabric of space-time itself. The leading theory suggests dark energy could be a property of empty space, a kind of anti-gravity that grows stronger as the universe expands. But there's a problem. When physicists calculate how much energy empty space should contain, their predictions are off by a factor of 1 followed by 120 zeros. That's not just a rounding error, it's the largest discrepancy in science. Some researchers propose alternative explanations, like a fifth fundamental force or even flaws in Einstein's equations. Others speculate that dark energy might not be constant at all, but evolving over time, which could mean the fate of the universe is even stranger than we thought. And that's the real stakes of this mystery. If dark energy continues to dominate, the universe will expand forever, growing colder and darker until galaxies vanish over the cosmic horizon. But if it strengthens unpredictably, it could lead to the Big Rip, where even atoms are torn apart in a violent end. The more we learn, the clearer it becomes. Dark energy isn't just a puzzle. It's the key to understanding whether the cosmos will fade quietly into the night or meet a far more dramatic fate. For now, it remains the ultimate cosmic wildcard, reminding us that the universe still has secrets we've only begun to uncover. Hidden behind the thick veil of stars and dust in our own Milky Way lies one of the universe's most perplexing enigmas, the Great Attractor. Picture this: thousands of galaxies, including our own, are being pulled toward a single point in space like moths to a flame, moving at speeds of over 2 million kilometers per hour. Yet we can't see what's tugging them. This colossal gravitational force, lurking in the direction of the constellations Centaurus and Hydra, defies explanation, leaving astronomers scrambling to uncover its secrets. For decades, the Great Attractor remained invisible to telescopes because it sits in what's called the zone of avoidance, a region obscured by the dense gas and dust of our galaxy's disk. It wasn't until the 1970s that scientists noticed something bizarre. Galaxies in our cosmic neighborhood weren't just drifting apart due to the universe's expansion. Instead, they were all streaming toward the same unseen destination. The discovery sent shockwaves through the astronomy community. How could something so massive stay hidden? What kind of structure could wield such gravitational power? Early theories suggested the Great Attractor might be a supercluster, a dense knot of galaxies with enough combined mass to pull others toward it. But when researchers finally peered through the Milky Way's obscuring dust using infrared and radio telescopes, they found something even more astonishing. The Great Attractor wasn't the end of the story. Beyond it lies an even larger structure, the Shapley Supercluster, a gargantuan assembly of galaxies 8,000 times more massive than the Milky Way. Could this be the true source of the pull, with the Great Attractor merely a waypoint in our cosmic journey, or is there something even stranger at work? Some scientists speculate that the Great Attractor might be a sign of larger, unseen structures, vast concentrations of dark matter, weaving the universe into a hidden architecture we're only beginning to map. Others wonder if it's evidence of exotic phenomena, like cosmic strings or defects in the fabric of space-time left over from the Big Bang. Every new observation deepens the mystery, revealing a universe far more interconnected and dynamic than we ever imagined. The hunt for answers isn't just about satisfying curiosity. Understanding the Great Attractor could rewrite the rules of galactic motion, revealing how matter clumps together on the largest scales and how dark matter shapes the cosmic web. It's a reminder that even in our own galactic backyard, there are forces at work beyond our sight, pulling the strings of the cosmos in ways we're only starting to comprehend. As telescopes grow more powerful and probes venture deeper into the unknown, one thing is certain: the Great Attractor won't stay hidden forever, and when its secrets finally come to light, they may change our place in the universe forever. One of the most electrifying cosmic mysteries happens in the blink of an eye: fast radio bursts. These fleeting blasts of radio waves last just milliseconds, but in that instant, they unleash as much energy as the sun does over 80 years. First detected in 2007, these cosmic flashes arrive without warning, often from billions of light-years away, and then vanish as suddenly as they appeared. The strangest part: some burst once and are never heard from again, while others repeat in erratic patterns, like a celestial Morse code no one can decipher. So where do these intense bursts come from? One leading suspect is Magneta's super-dense, highly magnetized neutron stars that spin rapidly, cracking under immense pressure like a cosmic bell ringing across the universe. When their crusts snap, they could release titanic flares of energy capable of producing fast radio bursts. But not all bursts fit this explanation. Some repeat in ways magnetas shouldn't, while others seem too energetic even for these extreme objects. That's led to wilder theories. Could they be the aftermath of colliding black holes or neutron stars? Or more provocatively, are we picking up artificial signals from advanced civilizations? The idea isn't as far-fetched as it sounds. In 1967, astronomers discovered pulsars and initially dubbed them LGM signals, short for little green men, before realizing they were natural phenomena. Fast radio bursts reignited that same debate when one, named FRB 121102, was found repeating from a dwarf galaxy 3 billion light-years away. The pattern didn't match any known astrophysical process, sparking speculation about alien megastructures or interstellar beacons. While most scientists lean toward natural explanations, the sheer variety of fast radio bursts keeps the question alive. Every new detection adds a twist to the puzzle. Some bursts arrive with a telltale sizzle, a dispersion effect that reveals how much material they've traveled through, acting like a cosmic ruler to map the universe's hidden matter. Others, like FRB 2020-0414, erupt with unprecedented clarity, offering astronomers pristine data to dissect. Then there's the oddball FRB 190520, which seemed to come from a relatively nearby spiral galaxy, challenging the assumption that all bursts originate in distant, chaotic environments. What makes fast radio bursts so thrilling isn't just their mystery, it's what they reveal about the universe. Each burst is a lighthouse in the cosmic dark, illuminating the invisible gas between galaxies and testing the limits of physics. Whether they're magnetars, collisions, or something even stranger, one thing is certain: solving their riddle won't just explain these fleeting signals. It could rewrite what we know about the most extreme environments in existence. Until then, they remain the universe's most enigmatic flashes, brief, brilliant, and utterly unpredictable. The universe is unimaginably vast, with billions of planets orbiting in the so-called Goldilocks zone, where conditions are just right for life to emerge. Given those odds, the cosmos should be teeming with civilizations, their signals buzzing across the galaxy like a cosmic internet. Yet when we listen, all we hear is silence. This glaring contradiction is the Fermi Paradox, named after physicist Enrico Fermi, who famously asked, "Where is everybody? If life is common, why does the universe feel so empty?" The answers we're uncovering, or failing to uncover, could reshape everything we think we know about our place in the grand scheme of existence. Consider the numbers for a moment. Our Milky Way alone contains hundreds of billions of stars, many with planets in habitable orbits. Even if only a tiny fraction of those worlds developed life, and an even smaller fraction gave rise to intelligent species, the galaxy should still host countless civilizations. Some estimates suggest there could be at least 36 advanced societies in our cosmic neighborhood right now. So why haven't we detected a single whisper of their presence? One unsettling possibility is that intelligent life is extraordinarily rare. Maybe the conditions needed for complex life are so precise: stable planetary climates, protective magnetic fields, the right mix of elements, that Earth is a cosmic fluke. Or perhaps life is common, but intelligence is the bottleneck. Dinosaurs ruled our planet for over 160 million years without developing technology. What if most worlds never evolve beyond microbial slime or simple creatures? Then there's the darker interpretation. Advanced civilizations might not last long enough to be detected. Climate disasters, nuclear war, rogue artificial intelligence, any of these could snuff out a society shortly after it develops the technology to broadcast its existence. If this is the norm, the universe could be littered with the ruins of civilizations that burned brightly, then vanished. But what if the silence isn't a sign of absence, but of something far stranger? Some scientists speculate that advanced civilizations might avoid broadcasting their presence, hiding from potential threats. Others propose they've moved beyond radio waves, communicating in ways we can't yet perceive, through quantum entanglement or manipulating space-time itself. There's even the eerie zoo hypothesis, the idea that Earth is deliberately left undisturbed, like an exhibit in a galactic wildlife preserve. The search for answers is accelerating. Projects like SETI scan the skies for technosignatures, radio signals, laser pulses, even megastructures like Dyson spheres. Meanwhile, telescopes hunt for biosignatures in exoplanet atmospheres, traces of oxygen or methane that could hint at life. Yet every empty result deepens the paradox. What makes the Fermi Paradox so profound isn't just the question of alien life, it's what it says about us. If we're alone, that's a humbling responsibility. If we're not, the silence might be a warning. Either way, the universe seems to be whispering a mystery we're only beginning to hear. And until we solve it, the stars will keep their secrets, leaving us to wonder who or what might be staring back. Imagine a black hole not bound to any galaxy, drifting through the void like a cosmic phantom. This is the terrifying reality of rogue black holes. Unlike the supermassive black holes that anchor galaxies at their cores, these lone wanderers roam interstellar space, invisible until their gravity warps the fabric of reality around them. Their existence paints a picture of chaos galactic collisions, violent ejections, and celestial upheavals that flung them into the abyss. And the scariest part, they could be far more common than we ever realized. So how does a black hole go rogue? Picture two galaxies merging in a slow-motion dance over billions of years. As their central supermassive black holes spiral toward each other, they release gravitational waves, ripples in space-time, that can kick one of them outward at speeds over 5,000 kilometers per second. That's fast enough to escape its galaxy entirely, leaving it to drift forever in the darkness. But that's not the only origin story. Some rogue black holes might be primordial, born in the extreme density of the early universe before galaxies even existed, lurking unseen for eons. Detecting these invisible monsters is like finding a needle in a cosmic haystack. Without a glowing accretion disk or orbiting stars to betray their presence, they reveal themselves only through subtle distortions. When a rogue black hole passes between us and a distant star, its gravity bends the starlight like a lens, briefly magnifying the star's brightness, a phenomenon called microlensing. In 2011, astronomers witnessed this exact scenario. A star in the Milky Way's bulge suddenly flared, its light warped by an invisible object roughly 7 times the mass of our Sun. The culprit, a solitary black hole, drifting unseen just 5,000 light-years away. But here's where it gets even stranger. Simulations suggest there could be hundreds of millions of rogue black holes hiding in our galaxy alone, far outnumbering the ones tethered to stars or galactic centers. Some might be as small as a city, yet way more than our Sun, while others could rival supermassive black holes in scale. If even a fraction of these predictions are true, the cosmos is far more dynamic and dangerous than we imagined. What makes rogue black holes so fascinating isn't just their stealth. They're cosmic time capsules holding clues to the universe's most violent events. By studying their trajectories and masses, scientists can piece together the history of galactic collisions, the behavior of gravity in extreme environments, even the nature of dark matter. And if primordial black holes exist, they could be the missing link to understanding the universe's birth. Yet for all their mystery, one question looms largest: what happens if one gets too close? A rogue black hole passing through our solar system would wreak havoc, distorting planetary orbits or hurling worlds into the void. But don't panic, the chances are astronomically low. Space is vast, and these dark wanderers are few and far between. Still, their existence is a humbling reminder. The universe is full of unseen forces, moving in the shadows, shaping the cosmos in ways we're only beginning to grasp. And as our telescopes grow sharper, who knows what other dark travelers we might find lurking just beyond the edge of sight. In the summer of 1977, a radio telescope in Ohio picked up something extraordinary, a burst of radiation so powerful and peculiar that the astronomer who discovered it scrawled, "Wow." In red ink on the printout, that single word would come to define one of the most tantalizing mysteries in the search for extraterrestrial intelligence. The signal lasted 72 seconds, blasting in at a frequency of 1,420 MHz, a band where cosmic noise is minimal and where scientists had theorized an alien civilization might broadcast. It came from the direction of the constellation Sagittarius, then vanished without a trace. Despite 40 years of follow-up observations, no one has ever detected it again. What made the WOW signal so electrifying wasn't just its strength, it was its structure. The signal ramped up in intensity, peaked, then faded symmetrically, exactly as you'd expect if a narrow beam transmission, like a lighthouse sweep, passed over Earth. Natural phenomena like comets or stellar flares don't behave this way. Even more intriguing, the frequency matched the hydrogen line, a universal channel astronomers had long suggested aliens might use to communicate, since hydrogen is the most abundant element in the cosmos. The odds of a natural event mimicking these traits seemed vanishingly small. Yet here's the frustrating twist: without a repeat signal, scientists can't confirm its origin. Some argue it might have been a reflected human transmission, bouncing off space debris. Others point to two comets that later passed through the same region, suggesting their hydrogen clouds could have been the source, though critics note the comets weren't there in 1977. Then there's the haunting possibility that it was a one-time beacon, a fleeting hello from a civilization that's since gone silent. The WOW signal's legacy isn't just about what it was, it's about how it reshaped our approach to the cosmos. It galvanized SETI researchers, proving that a single anomaly could ignite decades of curiosity. Modern projects now scan thousands of frequencies simultaneously, armed with AI to catch fleeting signals humans might miss. And though we may never solve the original mystery, its whisper continues to remind us, in a universe this vast, the next wow moment could be just one scan away. Imagine two particles born from the same event, separated by billions of light years, yet when you change the state of one, its partner instantly mirrors that change, no matter how far apart they are. This isn't science fiction, it's quantum entanglement, a phenomenon so bizarre even Einstein called it spooky action at a distance. At the quantum level, particles can become linked in such a way that measuring one immediately determines the properties of the other, as if they're connected by an invisible thread that defies the speed of light. And here's the kicker: experiments have proven this happens, whether the particles are across a lab or on opposite sides of the galaxy. How is this possible in a universe where nothing is supposed to travel faster than light? The answer lies in the strange rules of quantum mechanics, where particles exist in a haze of probabilities until observed. Entanglement occurs when particles interact in a way that their states become interdependent. Spin, polarization, or other quantum properties are tied together. What baffles scientists isn't just the instant connection, but the fact that no known force or signal mediates it. It's as if the universe has a hidden layer where distance doesn't matter, a cosmic cheat code that bypasses space-time itself. Recent breakthroughs have taken entanglement out of the lab and into space. In 2017, China's Misha satellite sent entangled photons to ground stations over 1,200 kilometers apart, smashing previous distance records. The particles stayed linked, proving entanglement survives even in the harsh environment of orbit. These experiments aren't just academic curiosities, they're paving the way for unhackable quantum encryption and networks where information leaps between points without passing through the middle. But could we ever use entanglement for faster-than-light communication? As tantalizing as it sounds, the answer for now is no. While changes to one particle affect its twin instantly, the outcome is random. You can't encode a message in that randomness because the recipient wouldn't know what was sent until you compared results through conventional, slower-than-light means. That hasn't stopped theorists from dreaming, though. Some speculate that advanced civilizations might have cracked the code, using entanglement in ways we can't yet imagine. The real game-changer lies in quantum computing. Entangled particles could form the backbone of machines that solve problems in minutes, which would take classical computers millennia. From simulating complex molecules for life-saving drugs to cracking encryption that guards today's internet. Companies like Google and IBM are already racing to build these systems, harnessing entanglement to perform calculations that defy classical logic. What makes quantum entanglement so revolutionary isn't just the technology it enables, it's the philosophical shake-up. If particles can influence each other across cosmic distances, what does that say about the nature of reality? Are space and time just illusions with deeper connections hidden beneath? Every experiment pulls back another corner of the curtain, revealing a universe far more interconnected and far stranger than we ever dared to dream. And as we stand on the brink of a quantum revolution, one thing is clear: the spookiest actions might just hold the keys to tomorrow's greatest breakthroughs. On October 19, 2017, the Pan-STARRS telescope in Hawaii spotted something extraordinary, a faint dot of light moving too fast to belong to our solar system. This was Oumuamua, the first confirmed visitor from interstellar space. Its name, meaning scout in Hawaiian, couldn't have been more fitting. Here was an object that had traveled through the void between stars for millions, perhaps billions, of years before briefly crossing our cosmic doorstep. But what made Oumuamua unforgettable wasn't just its origin. It was how utterly strange it behaved. First, there was its shape. Most asteroids and comets are roughly spherical or lumpy, but Oumuamua was different. Observations suggested it was elongated, possibly 10 times longer than it was wide, like a cosmic cigar tumbling through space. Nothing in our solar system matches this profile. Then came the real shocker. As it sped away from the sun, Oumuamua accelerated slightly, as if pushed by an unseen force. Comets do this when their ices vaporize, forming a visible tail, but Oumuamua showed no such tail or coma. It was as if this object had its own rules, defying every expectation. Theories erupted like a scientific supernova. Some argued it was a rare type of dark comet, made of hydrogen ice that vaporized invisibly. Others proposed it was a shard of a Pluto-like world, shattered by a distant collision. But the most provocative idea came from Harvard astrophysicist Avi Loeb, who suggested Oumuamua might be artificial, a discarded light sail or probe from an advanced civilization. The notion wasn't entirely fringe. Its unusual acceleration matched how a thin, reflective object would behave under sunlight's push. Still, most scientists leaned toward natural explanations, emphasizing how little we know about interstellar objects. The tragedy of Oumuamua is that we saw it too late. By the time telescopes spotted it, the visitor was already racing out of the solar system, leaving astronomers scrambling to gather scraps of data. Had we detected it earlier, probes could have intercepted it, giving us answers instead of riddles. But even in its fleeting visit, Oumuamua revolutionized astronomy. It proved interstellar objects pass through our neighborhood more often than we thought, and some, like the icy comet Borisov in 2019, even arrive with recognizable features. What lingers isn't just the mystery of what Oumuamua was, but what it represents. If such oddities are common, our solar system might be full of unnoticed interstellar travelers, each carrying secrets from distant stars. Future telescopes like the Vera Rubin Observatory will scan the skies for more of these cosmic nomads, and next time we'll be ready to chase them, to study them, and perhaps to finally understand what strange wonders sail the darkness between the stars. Until then, Oumuamua remains a tantalizing glimpse into the vast unknown, a silent messenger from realms we've only begun to explore. Black holes aren't just cosmic vacuum cleaners, they're information shredders, and that's a problem physics has been wrestling with for decades. Here's the puzzle. Quantum mechanics, the rulebook for the subatomic world, says information can never be truly destroyed. It might get scrambled or hidden, but in principle, you could always reverse engineer the past. Yet black holes, those gravitational monsters born from Einstein's theory of relativity, seem to break this rule. When matter falls in, it's crushed beyond recognition, and when the black hole eventually evaporates via Hawking radiation, all traces of what fell in vanish forever. Poof, gone. That's the black hole information paradox in a nutshell, a direct clash between the two pillars of modern physics, with the universe itself caught in the crossfire. Let's unpack why this is such a headache for scientists. Imagine burning a book. The pages turn to ash, the ink fades, but in theory, if you could track every molecule of smoke and heat, you could reconstruct the original text. Quantum mechanics insists reality works this way. Information is preserved even if it's messy. Now imagine tossing that book into a black hole. According to relativity, the book's atoms are stretched into spaghetti, then crushed at the singularity, a point of infinite density where the laws of physics break down. Decades later, when the black hole radiates away, all that emerges is a faint, featureless glow of Hawking radiation. No ashes, no smoke, no hidden clues. The book's information isn't just scrambled, it's erased from existence. Two flawless theories, one impossible contradiction. The stakes couldn't be higher. If information really is lost in black holes, quantum mechanics needs a rewrite. If it isn't, Einstein's relativity might be incomplete. Physicists have proposed wild solutions to bridge the gap. One leading idea is the holographic principle, which suggests all the information swallowed by a black hole isn't destroyed but smeared across its event horizon like a cosmic fingerprint, encoded in tiny Planck-scale pixels. Another theory, called firewalls, posits a searing wall of energy at the event horizon that vaporizes incoming matter, preserving information but violating relativity's prediction that falling into a black hole should feel uneventful. Then there's the even more radical notion that black holes don't have singularities at all. Instead, they're knots of spacetime so tangled that they birth new universes, carrying the information elsewhere. The paradox isn't just academic, it's a battleground for the future of physics. Solving it could reveal how spacetime emerges from something deeper, like a cosmic quantum code. It might even hint at a theory of everything, a framework to unify gravity and quantum mechanics. But for now, black holes keep their secrets, challenging us to think bigger, dig deeper, and question everything we thought we knew. And in that tension between what we understand and what lurks beyond the event horizon, lies one of science's greatest adventures. In the vast emptiness of space, where the laws of physics are supposed to be predictable, two tiny spacecraft defied expectations in the strangest way. NASA Pioneer 10 and 11, launched in the early 1970s to explore the outer solar system, began slowing down more than they should have. Not by much, just a fraction of a nanometer per second squared, but over decades and billions of miles. That tiny discrepancy added up to thousands of miles of drift. Scientists called it the Pioneer Anomaly, and for 30 years it gnawed at physicists like a cosmic itch they couldn't scratch. At first, researchers assumed it was a simple engineering quirk, maybe heat, radiating unevenly from the probe's power systems, was giving them an invisible push. But when they crunched the numbers, thermal radiation only accounted for part of the deceleration. That left two unsettling possibilities. Either some unknown force was acting on the pioneers, or our understanding of gravity itself had a gap. The implications were staggering. If gravity behaved differently in the outer solar system, it could mean Einstein's theory of relativity needed an update, or that dark matter was exerting an undetected pull. The mystery deepened when later missions, like the Voyagers and New Horizons, didn't experience the same anomaly. Why would only the pioneers be affected? Some theorists proposed exotic explanations, hidden dimensions, quantum foam altering spacetime, even the gravitational influence of parallel universes. Others argued for more mundane causes like fuel leaks or instrument errors, but without definitive proof, the Pioneer Anomaly became a cautionary tale, a reminder that even in our own cosmic backyard, nature might still have tricks up its sleeve. Then, in 2012, a breakthrough. A team of researchers painstakingly reconstructed the probe's heat signatures using decades-old data and discovered something surprising. The way heat radiated off the spacecraft's nuclear power sources could, in fact, explain most of the anomaly. It wasn't a flaw in relativity or a new force, just an overlooked thermal effect. Case closed, not quite. Even after accounting for heat, a tiny fraction of the deceleration remained unexplained. Was it noise in the data or something deeper? What makes the Pioneer Anomaly so fascinating isn't just the mystery itself, it's what it reveals about how science works. For decades, it forced physicists to question their assumptions, to scour the data for overlooked details, and to entertain wild ideas. It showed how even the smallest discrepancy can lead to monumental questions, and while most scientists now consider it solved, that lingering uncertainty keeps the door open, just a crack, for the next great cosmic surprise. After all, if we missed something as subtle as heat radiation in our own solar system, what else might be hiding in the shadows, waiting to upend everything we think we know? Beyond the orbit of Neptune, where sunlight is a faint memory and temperatures plunge near absolute zero, something strange happens. The Kuiper Belt, that icy graveyard of primordial leftovers from the solar system's birth, simply ends. Astronomers call it the Kuiper Cliff, and it's one of the most baffling boundaries in our cosmic neighborhood. Imagine tossing rocks into a pond and watching them ripple outward, only for the ripples to suddenly stop as if hitting an invisible wall. That's what we see here, thousands of small, frozen objects orbiting the sun, then nothing. The drop-off is so sharp, it defies everything we know about how planetary systems form. The Kuiper Belt was supposed to fade gradually, with smaller, scattered objects stretching far into the darkness. Instead, around 50 astronomical units from the Sun, roughly 7.5 billion kilometers, the belt's population plummets. This isn't just a statistical fluke. Observations from telescopes like Hubble and Subaru confirm the cliff is real, and it's forced scientists to confront two spine-tingling possibilities. Either our models of the early solar system are missing a critical piece, or something massive is lurking out there, its gravity shearing the belt like an invisible pair of cosmic scissors. Could that something be Planet 9? The hypothetical world, first proposed in 2016, would weigh 5 to 10 times Earth's mass and orbit hundreds of times farther than our planet. Its gravitational pull could explain not just the Kuiper Cliff, but also the peculiar, clustered orbits of distant objects like Sedna, which swing far beyond the belt on paths that shouldn't exist without an unseen disruptor. The evidence is circumstantial but compelling, like finding footprints in the snow leading to an empty horizon. Yet Planet 9 isn't the only explanation. Some researchers argue the cliff might be a fossilized edge, a relic from the solar system's violent infancy. In this scenario, the young sun's birth cluster, a temporary family of sibling stars, could have stripped away the outer Kuiper belt billions of years ago, leaving behind a stark boundary. Others speculate that passing stars or rogue planets might have stolen the missing objects, a cosmic heist lost to time. There's even a radical idea that the cliff marks where the sun's magnetic bubble, the heliosphere, begins to weaken, allowing interstellar forces to erode smaller bodies. The hunt for answers is heating up. New telescopes like the Vera Rubin Observatory, set to begin sweeping the skies in the next few years, could finally spot Planet 9 if it exists, or rule it out entirely. Meanwhile, missions like NASA's Interstellar probe aim to venture beyond the Kuiper Cliff, giving us our first direct look at this uncharted frontier. What they find could rewrite textbooks. If the cliff hides a planet, it would be the first new world discovered in our solar system since Neptune in 1846. If it doesn't, we'll need to rethink how planetary systems evolve at their edges. But here's the real intrigue. The Kuiper Cliff isn't just about what's missing. It's a window into the solar system's past and a test of our cosmic imagination. Every unexplained boundary whispers the same truth. We're still mapping our own backyard, and the universe loves to surprise us. Whether the answer is a hidden world, a ghostly gravitational echo, or something even stranger, one thing's certain: the edge of the solar system is anything but empty. It's a mystery waiting to be solved. The moon today is a silent, airless world, its surface scarred by billions of years of impacts. But buried in its rocks lies a shocking secret. Our lifeless companion once had a magnetic field rivaling Earth's in strength. This discovery sent shockwaves through planetary science because, according to everything we know, the moon shouldn't have been capable of such a feat. Earth's magnetic field is generated by our churning molten core, a dynamo powered by our planet's vast size and heat. The moon, just 1/80th of Earth's mass, should have cooled and solidified too quickly to sustain that kind of activity. Yet lunar samples collected during the Apollo missions tell a different story. Trapped within their crystals are traces of a magnetic field that lasted for over 1 billion years. How could something so small pack such a powerful cosmic punch? One leading theory points to catastrophe literally. The moon was born from chaos when a Mars-sized object called Theia smashed into the early Earth, flinging debris into orbit that later coalesced into our satellite. That apocalyptic collision might have left the newborn moon scalding hot, with a molten core spinning violently from the impact's leftover energy. Like a top set spinning by a giant's hand, this motion could have jump-started a temporary magnetic dynamo, one that faded as the moon cooled. But here's the catch: simulations show this impact dynamo would have lasted only a few thousand years, not the eons the rock record suggests. That's led scientists to propose even wilder ideas. Perhaps the moon's core was enriched with radioactive elements like potassium and thorium, whose decay kept it molten far longer than expected. Or maybe its orbit played a role. Early gravitational tugs from Earth could have stretched and squeezed its interior like putty, generating heat through friction. There's even a radical notion that the moon once had a massive liquid iron layer above its core, sloshing like water in a spinning bowl, creating a magnetic field through sheer motion. The implications go far beyond lunar history. If small bodies like the moon can generate magnetic fields through unconventional means, it changes how we view other worlds. Mercury, despite its tiny size, has a weak magnetic field today. Could its past have been more active? Even asteroids like Vesta show signs of ancient magnetism, hinting at a solar system buzzing with magnetic activity in its youth. Unlocking the moon's secret could rewrite the rules for how planetary dynamos form, revealing that size isn't always destiny. But the biggest mystery remains: why did the moon's field vanish? Around 1 billion years ago, the magnetic traces in lunar rocks simply stop. Did the core finally freeze solid? Did a colossal impact disrupt its flow? Or did some unseen cosmic switch flip, silencing the moon's invisible shield forever? Every new lunar mission, from India's Chandrayaan probes to NASA's upcoming Artemis landings, brings us closer to answers. And when we find them, they won't just illuminate the moon's past. They'll reveal how magnetism, that invisible cosmic force, shapes the destiny of worlds big and small across the universe. One of the biggest embarrassments in modern cosmology isn't a missing particle or a failed theory. It's a simple number that refuses to agree with itself. Scientists call it the Hubble constant, the rate at which the universe is expanding, and measuring it should be straightforward. But here's the catch: depending on how you measure it, you get wildly different answers. This discrepancy, known as the Hubble tension, has thrown cosmology into crisis, forcing researchers to confront the unsettling possibility that something fundamental in our understanding of the universe is wrong. Let's break down the numbers. One method relies on the cosmic microwave background, the afterglow of the Big Bang, which lets us calculate the expansion rate by studying the early universe's ripples. According to this approach, the Hubble constant should be around 67 kilometers per second per megaparsec. But when scientists use pulsating stars called Cepheids or exploding supernova as cosmic yardsticks, measuring distances in the more recent universe, the number jumps to roughly 73. That gap might seem small, but in the precise world of cosmology, it's catastrophic. Imagine two clocks, both built by master craftsmen, one ticking slightly faster than the other. Over centuries, the difference would be negligible, but over billions of years, it would rewrite history. The implications are staggering. If the measurements are correct and not just systematic errors, it means our standard model of cosmology, the carefully crafted recipe of dark matter, dark energy, and ordinary matter that explains everything from galaxy formation to the universe's fate, might be missing an ingredient. Some theorists suggest dark energy isn't constant but evolves over time, growing stronger or weaker in ways we haven't accounted for. Others propose exotic particles that interacted with light in the early universe, subtly altering the cosmic microwave background signals. Then there's the radical idea that gravity itself behaves differently on cosmic scales, a tweak that could upend Einstein's theory of relativity, but the boldest hypothesis of all. That we're seeing evidence of a shadow universe, a parallel cosmos whose gravity tugs on ours, distorting the expansion rate in ways we can't yet explain. It sounds like science fiction, but the Hubble tension has gotten scientists so desperate that even fringe ideas are getting serious consideration. After all, when the numbers refuse to add up, sometimes you need to rewrite the equation. What makes this crisis so thrilling isn't just the mystery, it's the opportunity. Every great upheaval in cosmology, from the discovery of the expanding universe to the shock of dark energy, started with a nagging inconsistency. The Hubble tension could be the next revolution in disguise, a clue that the universe is stranger, richer, and more complex than we ever imagined. Until we crack it, one thing is certain: the cosmos is still holding back its deepest secrets, and the answers, when they come, might change everything. We think of the universe's ordinary matter, the stuff that makes up stars, planets, and even us, as the part we understand best. But here's the cosmic irony: roughly half of it has gone missing. Not dark matter, not exotic particles, but plain old protons and neutrons, the building blocks of everything tangible. Scientists call this the missing Baryon problem, and it's one of the most humbling gaps in our cosmic inventory. If the math is right, there should be twice as much ordinary matter out there as we've actually detected. So where is it hiding? The answer might lie in the darkest, emptiest reaches of space, the voids between galaxies. Picture the universe as a vast web with galaxies strung along invisible threads of dark matter. The spaces between those threads aren't truly empty. They're filled with wisps of million-degree gas, so hot and diffuse they're almost transparent. These filaments, part of the so-called warm-hot intergalactic medium, could be the universe's lost and found for baryons. The gas is too faint to see with optical telescopes, and so thinly spread that a cubic meter might contain just a single atom. Yet across billions of light years, it adds up to a staggering amount of missing mass. The challenge is proving it's there. Astronomers have turned to ingenious tricks, like using distant quasars as cosmic flashlights. When light from these blazing galactic cores passes through the intergalactic fog, certain wavelengths get absorbed, leaving fingerprints in the spectrum. It's like detecting a whisper in a hurricane, but over the past decade, these fingerprints have revealed traces of oxygen and other elements, proof that the filaments are real. Even more compelling, the gas's temperature and distribution match predictions from simulations of the cosmic web, but the mystery isn't fully solved. Some of the missing baryons might be hiding closer to home in our own galactic neighborhood. The Milky Way's halo could be swathed in a shroud of hot gas, too faint to spot directly. Others might lurk in low-mass galaxies or dwarf systems too dim for current telescopes. And then there's the unsettling possibility that our accounting is off, that baryons behave in ways we haven't anticipated, or that the universe's early chemistry left clues we're only beginning to decode. What makes this hunt so crucial isn't just about tallying cosmic ingredients. Those missing baryons are the glue of the cosmic web, the scaffolding that shapes how galaxies form and cluster. Without them, our models of the universe's structure are like blueprints with half the lines erased. New telescopes, like the upcoming Athena X-ray Observatory, aim to map these hidden filaments in unprecedented detail, turning whispers into shouts. And when we finally close the gap, we won't just solve a puzzle, we'll rewrite the story of how the ordinary becomes extraordinary, and how the seen and unseen weave the universe together. The cosmic microwave background should be the most boring picture in the universe, a near-perfect snapshot of the infant cosmos, frozen in time and uniformly splashed across the sky. But when scientists peeled back the layers, they found something that sent chills down their spines. The universe appears to have a spine of its own. Dubbed the axis of evil, this bizarre pattern in the CMB shows unexpected alignments that point in a preferred cosmic direction, as if the universe has a hidden set of tracks guiding its expansion. The discovery isn't just puzzling, it's a direct challenge to one of cosmology's most sacred principles, isotropy, the idea that the universe should look the same in every direction. What makes the axis of evil so unnerving is how precisely it defies expectations. When the Planck satellite mapped the CMB's temperature fluctuations with unprecedented detail, researchers noticed eerie correlations between hot and cold spots along a specific axis stretching across the sky. It's as if someone drew a faint arrow through the cosmos, marking a direction that somehow influenced the Big Bang's afterglow. The odds of this happening by chance? Less than 1 in 1,000. Either we're witnessing the mother of all statistical flukes, or there's a fundamental crack in our understanding of cosmic beginnings. Theories attempting to explain this anomaly range from the cautious to the mind-bending. Some suggest it could be an artifact of our local environment. Perhaps the gravitational pull of nearby superclusters is distorting the CMB in ways we haven't fully accounted for. Others propose more radical ideas, like cosmic defects left over from a phase transition in the early universe, where space-time itself crystallized with imperfections, much like cracks forming in ice. The most tantalizing and controversial possibility, that the axis of evil is a fossil imprint from before the Big Bang, a relic of some deeper physics that set the stage for our universe's birth. If that last idea sounds like science fiction, consider this. Many cosmologists now take pre-Big Bang scenarios seriously. Theories like loop quantum gravity or string theory's brain worlds allow for a before, where our universe emerged from the collapse or collision of a prior cosmos. In such models, the axis of evil could be a cosmic fingerprint, a directional memory of that primordial event. It's as if we're staring at a photograph and realizing the camera itself left a shadow in the frame. The stakes couldn't be higher. If the axis of evil is real and not an illusion, it means the universe isn't just slightly lopsided, it's fundamentally anisotropic, with preferred directions woven into its fabric. This would force us to rewrite not just cosmology textbooks, but the very equations that describe reality's origins. Future CMB experiments, like the proposed CMB S4 project, aim to settle the debate with even finer measurements. Until then, the axis of evil remains cosmology's most unsettling riddle, a whisper from the void that the universe might not be playing by the rules we thought we knew. And if there's one thing history teaches us, it's that when the cosmos breaks its own rules, the discoveries that follow are nothing short of revolutionary. Most stars flicker gently, their light dimming and brightening in predictable rhythms. But then there's KIC 8462852, better known as Tabby's star. This unassuming point of light in the constellation Cygnus doesn't just flicker, it plunges. At random intervals, its brightness drops by as much as 22%, as if something colossal is passing in front of it, something far larger than any planet. These aren't the tidy, repeating dips of an orbiting world. They're chaotic, asymmetrical, and utterly baffling. When astronomers first spotted this behavior in data from NASA's Kepler telescope, it sent shockwaves through the scientific community. Stars like this shouldn't exist, and yet here it is, defying every expectation. The initial theories were mundane enough. Maybe a swarm of comets, shattered by a collision, was drifting in front of the star, blocking its light in irregular clumps. Or perhaps an enormous dust cloud, left over from some ancient cosmic catastrophe, was spiraling inward. But there was a problem. None of these explanations fully matched the data. Comets couldn't explain the sheer depth of the dimming, and dust should have left a telltale infrared signature, one that later observations failed to detect. That's when things got interesting. Enter the most provocative idea of all, alien megastructures, specifically a Dyson swarm, a hypothetical array of solar collectors built by an advanced civilization to harness their star's energy. The concept, first proposed by physicist Freeman Dyson in the 1960s, suggests that a sufficiently advanced society might encircle its sun with orbiting panels or habitats, capturing its light in ways that would cause exactly the kind of erratic dimming we see with Tabby's star. It was a long shot, but in the absence of a clear natural explanation, even the wildest possibilities had to be considered. Of course, extraordinary claims require extraordinary evidence, and Tabby's star hasn't given up its secrets easily. Follow-up studies have turned up more questions than answers. Some observations suggest the star is gradually fading over decades, a phenomenon no known stellar behavior fully explains. Others hint at fine dust particles in the system, though how they're being replenished remains a mystery. And then there's the star's bizarre color changes, which don't fit neatly into any model. The real lesson of Tabby's star isn't just about aliens or cosmic oddities. It's about how science grapples with the unknown. When faced with something that defies easy explanation, researchers don't just throw up their hands, they dig deeper, test new ideas, and challenge old assumptions. Every observation, every failed hypothesis, brings us closer to understanding not just this one strange star, but the broader tapestry of stellar behavior. And who knows, the answer, when it finally comes, might be something no one has even imagined yet. Until then, Tabby's star remains a brilliant reminder. The universe is full of surprises, and sometimes the most ordinary-looking things hide the most extraordinary mysteries. In the grand tapestry of the cosmos, where galaxies cluster like cities and filaments weave the universe into a vast web, there's a place where everything just stops. The Eridanus Supervoid isn't just empty, it's a staggering nothingness stretching over 1.8 billion light-years, a cosmic desert so vast it could swallow thousands of Milky Ways without a trace. But here's what really sends shivers down astronomers' spines. This void isn't just a blank spot. It's linked to one of the most perplexing anomalies in the cosmic microwave background, a mysterious cold spot where the afterglow of the Big Bang is noticeably dimmer. The odds of such a void existing by chance, less than 1 in 50. So what carved this hole in the universe, and why does it leave such a chilling fingerprint on the CMB? Picture the universe as a loaf of rising bread with galaxies as raisins scattered throughout. As space expands, you'd expect the raisins to spread somewhat evenly. But the Eridanus Supervoid is like a bizarre bubble where the dough barely rose at all, a region where matter didn't just thin out but seemingly vanished. Most voids are small, maybe 100 million light-years across. This one's 20 times larger, defying every model of cosmic structure formation. If voids this size exist, our theories about how gravity sculpts the universe might be missing a critical piece. The plot thickens when we look at the CMB Cold Spot. According to standard cosmology, photons from the Big Bang's afterglow should gain a tiny bit of energy when they pass through dense galaxy clusters and lose a bit in voids, an effect called the integrated Sachs-Wolf effect. But the Eridanus Supervoid's cold spot is far colder than this effect can explain. It's as if the void isn't just empty but somehow sucking energy from the CMB, leaving behind a shadow that shouldn't be there. Some theorists suggest this could be evidence of a cosmic defect, a crack in spacetime's fabric left over from the universe's earliest moments, like a frozen scar from when the laws of physics were still settling into place. Then there's the radical possibility that the supervoid isn't entirely empty. Instead, it might be filled with something that counteracts gravity, like dark energy in concentrated form, creating a repulsive force that pushed matter away. If true, it would mean dark energy isn't just a smooth background field but clumps and varies like matter, upending our current models. Others argue the cold spot might not be connected to the void at all, but a statistical fluke, or even, more provocatively, a bruise from a collision with another universe during cosmic inflation. What makes the Eridanus Supervoid so electrifying isn't just its size or its cold spot, but what it represents, a crack in cosmology's foundation. If voids this large can exist, our simulations of the cosmic web might need rewriting. If the cold spot is real, it could hint at physics beyond the standard model. And if it's all just a cosmic coincidence, that's almost stranger, forcing us to reckon with how much of the universe's structure is random and how much is shaped by forces we've yet to name. As telescopes like the Vera Rubin Observatory begin mapping the sky in unprecedented detail, one thing's certain: the biggest mysteries aren't always in the light. Sometimes they're in the voids between. Galaxies are supposed to follow certain rules. Dark matter provides the invisible scaffolding that holds them together, guiding their formation and preventing them from spinning apart. But in 2018, astronomers stumbled upon a cosmic rebel that breaks all the rules, NGC 1052DF2, a galaxy that appears to have no dark matter at all. At first, scientists assumed it had to be a mistake. How could something so fundamental just vanish? Yet repeated observations confirmed the impossible. This faint, ghostly galaxy moves as if it's barely feeling gravity's tug, its stars drifting leisurely through space without the extra pull dark matter should provide. The discovery sent shockwaves through astronomy, forcing us to confront a haunting question. If dark matter isn't universal, what does that mean for everything we thought we knew about how galaxies are born? The mystery starts with the galaxy's bizarre composition. Unlike most galaxies, which are dominated by dark matter's gravitational grip, DF2's motions can be explained almost entirely by the visible stars alone. Its globular clusters, dense groups of ancient stars orbiting the galaxy's core, move far slower than expected, as if the galaxy's gravity has been dialed down. Even more puzzling, DF2 isn't alone. several other oddball galaxies like DF4 have since been found with similarly missing dark matter, suggesting this isn't just a fluke. The implications are staggering. If dark matter can be absent, does that mean it's not woven into the fabric of galaxies after all? Or could these outliers be the result of some violent cosmic event that stripped them clean? One leading theory proposes a dramatic origin story. DF2 resides near a massive elliptical galaxy, NGC 1052, and might have been a victim of cosmic robbery. Billions of years ago, as it orbited its larger neighbor, tidal forces could have ripped away its dark matter while leaving the stars behind, like a thief stealing a shadow while leaving the body untouched. Computer simulations show such encounters are possible, but they'd require precise conditions. Alternatively, DF2 might have formed in an unusually sparse pocket of the early universe, where dark matter was too thinly spread to clump into galaxies normally. Instead, ordinary matter could have collapsed on its own, creating a rare dark matter-free anomaly. But the most radical idea challenges dark matter itself. Could DF2 be evidence that gravity behaves differently on galactic scales? Modified Newtonian dynamics, or MUND, is a controversial theory proposing that our understanding of gravity is incomplete, that at low accelerations the laws change in ways that mimic dark matter's effects. If true, DF2's strange behavior might not require invisible matter at all. Yet MUND struggles to explain other cosmic phenomena, like the Bullet Cluster, where colliding galaxies clearly separate from their dark matter halos. The debate rages on with DF2 at the center, a galactic enigma that refuses to fit neatly into any box. What makes this discovery so thrilling isn't just the mystery of one odd galaxy. It's the possibility that DF2 represents a hidden chapter in galactic evolution, one where the rules aren't as rigid as we assumed. Perhaps dark matter isn't the only way to build a galaxy. Or maybe these outliers are cosmic breadcrumbs leading us toward a deeper understanding of how dark matter interacts, or doesn't, with the visible universe. With every new observation, DF2 forces us to rethink the foundations of cosmology, proving once again that the universe's greatest teachers are often its most unexpected exceptions. And as telescopes peer deeper into the void, who knows what other rule-breaking galaxies might be waiting to challenge our view of the cosmos? The Boots void isn't just an empty patch of space. It's a cosmic anomaly so vast and desolate that astronomers call it the Great Nothing. Spanning over 300 million light-years, this spherical region of the universe contains only a handful of galaxies where there should be thousands. Picture a balloon the size of a stadium with just a few scattered grains of sand inside. That's the scale of emptiness we're dealing with. For comparison, a typical region of space that size would be teeming with galactic neighbors. But here, the darkness stretches uninterrupted, a yawning chasm in the fabric of the cosmos that defies our expectations of how matter should be distributed. What makes the Boots void so unsettling isn't just its emptiness, it's the mystery of how it got that way. One theory points to cosmic inflation, the rapid expansion of the universe moments after the Big Bang. During this explosive growth spurt, quantum fluctuations could have created uneven pockets of density, leaving behind ultra-sparse regions like this one. But there's a problem. Even the most extreme models of inflation struggle to explain a void this large. It's like finding a crater so big, no known impact could have created it. That's led to more dramatic speculation. Could something have swept through this region, clearing out galaxies like a cosmic broom? Some researchers propose that the void might be the aftermath of an ancient collision between our universe and another bubble universe during the multiverse's chaotic infancy. Others wonder if it's evidence of a super-advanced civilization, a Kardashev-type 3 civilization that harnessed the energy of galaxies, leaving behind an engineered emptiness. While these ideas stretch the imagination, they underscore how thoroughly the Boots void appends our assumptions. Normally, voids are surrounded by dense walls of galaxies like bubbles in foam. But the Great Nothing sits isolated, as if it's been carved out deliberately. The real challenge lies in mapping it. Galaxies within the void are so scarce and distant that even with powerful telescopes, we're left with more questions than answers. The few galaxies that do exist there seem oddly unfazed by their solitude, orbiting as if the void's gravitational pull is weaker than predicted. This has sparked debates about whether dark energy, the mysterious force accelerating the universe's expansion, might be concentrated here, pushing galaxies apart more aggressively. What's at stake isn't just curiosity about one strange region. If voids like Boots can't be explained by standard cosmology, it might mean our models of large-scale structure need a rewrite. Are there more of these great nothings lurking undetected? Could they be windows into exotic physics or relics of events we've yet to imagine? Every observation peels back another layer, revealing just how much of the universe's story is still written in shadows. And until we solve the riddle of the Boots void, its silence will keep echoing one undeniable truth: the cosmos is far stranger and far emptier than we ever dreamed. Imagine driving through space in a rocket, accelerating faster and faster, when suddenly the pitch-black void around you begins to glow with heat. That's the essence of the Unruh Effect, a bizarre prediction from quantum field theory stating that an accelerating observer should perceive empty space not as empty, but as a warm bath of radiation. To you, the universe would feel like a cozy sauna, while someone floating nearby at a constant speed would swear it's freezing cold. This isn't just a thought experiment. The math checks out, yet nearly 50 years after physicist William Unruh first proposed it, no one has ever detected this ghostly glow. Is it because the effect is impossibly faint, or could its elusiveness be hiding cracks in our understanding of reality? The Unruh Effect emerges from the same quantum weirdness that gives us Hawking radiation. Just as a black hole's gravity can pull virtual particles apart, creating real radiation at its event horizon, acceleration through empty space should do something similar. Virtual particles, fleeting quantum fluctuations that pop in and out of existence, would appear to an accelerating observer as real photons, their energy proportional to the acceleration. The catch: for the glow to be detectable, you'd need mind-bending acceleration. To feel even a lukewarm 1 degree Kelvin, you'd have to accelerate at 1 quintillion times the force of Earth's gravity. That's far beyond anything our technology can achieve, leaving the Unruh Effect trapped in the realm of theory. But here's where it gets even stranger. Some physicists argue the Unruh Effect isn't just a quirk of acceleration, it might be a window into quantum gravity. The effect hinges on how different observers perceive quantum fields, a tension that also lies at the heart of the conflict between Einstein's relativity and quantum mechanics. If we could detect it, even indirectly, it might reveal how these two frameworks stitch together at the universe's most fundamental level. Experiments are already pushing the boundaries. One approach uses ultra-strong lasers to mimic acceleration in the lab, while another tracks electrons in particle accelerators for telltale energy shifts. So far, nothing conclusive. The most tantalizing possibility: the Unruh Effect might not exist as predicted. If future experiments rule it out, it could force physicists to rethink quantum field theory itself. Maybe empty space doesn't respond to acceleration the way we thought, or perhaps our understanding of virtual particles is flawed. Either way, the hunt for this phantom glow isn't just about checking a box in quantum theory. It's about probing the edges of known physics, where the next great discovery might be hiding in the darkness, waiting to rewrite the rules. In the cosmic microwave background, that ancient echo of the Big Bang, there's a patch of sky that doesn't belong. Nestled in the constellation Eridanus, a region roughly 10 times the diameter of the full moon glows noticeably colder than its surroundings, a cosmic chill that defies easy explanation. Scientists call it the CMB Cold Spot, and it's not just a minor statistical blip. This anomaly is so pronounced that the odds of it arising by random chance are less than 1 in 100. Some researchers believe it could be the first tangible evidence of a reality beyond our own, a bruise left by a collision with another universe during the chaotic infancy of the cosmos. The cold spot's strangeness isn't just about temperature, it's also about scale. Most fluctuations in the CMB are tiny, the result of quantum ripples stretched across the sky by inflation. But this region is vast, nearly 2 billion light-years across, and its temperature dip is far sharper than standard models predict. One theory suggests it's the imprint of a cosmic texture defect, a kink in space-time left over from the universe's earliest moments, like a frozen wrinkle in the fabric of reality. These defects, predicted by some grand unified theories, would warp the surrounding space in ways that could explain the cold spot's unusual profile. Then there's the multiverse angle. If our universe is just one bubble in a frothing sea of inflationary space, it's possible another bubble once bumped against ours. The energy released in that collision would have left a distinct signature, a circular depression in the CMB, eerily similar to what we observe. It's a radical idea, but proponents point to the cold spot's shape and sharp edges as potential clues. Of course, skeptics argue it could still be a statistical fluke, or the shadow of an enormous supervoid, a region of space so empty that photons lose energy as they traverse it. Yet even the largest known voids can't fully account for the cold spot's intensity, leaving the door open to wilder possibilities. What makes this mystery so thrilling isn't just the science, it's the stakes. Confirming the cold spot as evidence of a multiverse would rank among the most profound discoveries in history, reshaping our understanding of existence itself. Future telescopes like the Simons Observatory and CMB S4 aim to study the spot with unprecedented precision, searching for telltale patterns in polarization or secondary distortions. Until then, this icy anomaly remains a tantalizing question mark, a whisper from the edge of the known cosmos. Whether it's a flaw in our models, a relic of cosmic violence, or a window into another reality, one thing is certain: the universe is still writing its strangest chapters, and the cold spot might just be the opening line. Far beyond Neptune's icy realm, where sunlight fades to a dim memory, something massive is tugging at the solar system's edge. Distant objects, icy worlds like Sedna and Biden, don't orbit the sun the way they should. Instead, their paths cluster in strange, tilted ellipses, as if an unseen hand is herding them. The math points to one startling possibility: a planet. Not just any planet, but a world up to 10 times heavier than Earth, lurking so far out that a single orbit could take 20,000 years. This is the Planet 9 hypothesis, and it's rewriting our map of the solar system's frontier. What makes this idea so compelling isn't just the orbital oddities, it's the scale of the mystery. The hypothetical Planet 9 wouldn't be some faint speck in a telescope. If it exists, it's a frozen giant, possibly resembling a super-sized version of Uranus or Neptune, with a gravitational reach vast enough to sculpt the trajectories of smaller bodies across billions of miles. Yet despite years of searching, it's remained invisible. That's because at such extreme distances, even a large planet reflects almost no sunlight, and its motion against the stars would be glacially slow. Spotting it would be like finding a single charcoal briquette hidden somewhere in a football stadium at night. The hunt has turned astronomers into cosmic detectives. Using simulations, researchers have traced how Planet 9's gravity would not only cluster distant orbits, but also tilt the entire solar system's plane slightly askew. Some even suggest it could explain the peculiar orbits of objects like the dwarf planet Gong, which swings far beyond Neptune on a path that defies easy explanation. Every new discovery in the Kuiper belt adds another clue, tightening the noose around where this hidden world might hide. Skeptics, of course, have alternative theories. Maybe the odd orbits are statistical noise, or perhaps the collective gravity of countless small icy objects is masquerading as a single massive one. But the more data we gather, the harder it becomes to explain the patterns without invoking Planet 9. The upcoming Vera Rubin Observatory, with its ability to scan the entire southern sky in unprecedented detail, could settle the debate once and for all, either by spotting the planet or ruling it out entirely. The implications of discovery would be staggering. Not only would it be the first new planet found in our solar system since 1846, but it could redefine how planetary systems form. Current models struggle to explain how a world this large ended up so far from the Sun. Was it flung outward by a gravitational slingshot with Jupiter in the solar system's violent youth? Or is it an exiled rogue planet captured from another star long ago? Until we find it or rule it out, Planet 9 remains the ultimate celestial ghost story, a shadow at the edge of our cosmic backyard. And whether it's real or not, the search itself has already revealed how much we still have to learn about the place we call home. After all, if something this big could be hiding in plain sight, what else might be waiting undiscovered in the dark? Black holes devour everything in their path, crushing matter into oblivion. But what if the universe has an equal and opposite reaction? Enter white holes, the theoretical yin to black holes' yang. While black holes trap light and matter behind an event horizon from which nothing escapes, white holes would do the exact opposite, violently expelling energy and matter while barring anything from entering. According to Einstein's equations of general relativity, these cosmic fountains should exist as perfectly valid solutions. Yet to this day, not a single confirmed white hole has ever been observed. So where are they, and if they're real, what mind-bending secrets might they hold? The concept of white holes isn't just science fiction, it's rooted in the same math that predicts black holes. If you take the equations describing a black hole and reverse the flow of time, you get a white hole. A region of space-time where matter erupts outward like a geyser, defying all attempts to approach it. Some theorists suggest that a white hole could be the other end of a black hole, spewing out what its counterpart devoured, potentially in another universe. This idea fuels wild speculation about wormholes, bridges between distant points in space-time, where a black hole's entrance might connect to a white hole's exit. But before we get too carried away, there's a glaring problem. No known physical process can create a white hole in our universe. Black holes form from collapsing stars, but white holes would require conditions so extreme they border on fantasy. One tantalizing possibility is that white holes could explain certain cosmic explosions. Gamma-ray bursts, the most energetic events since the Big Bang, release unfathomable amounts of energy in mere seconds. Could these be the death throes of white holes, blasting their contents into space in one final, catastrophic eruption? There's also the curious case of dark explosions, mysterious bursts of energy detected in deep space with no visible aftermath. If white holes exist, they might flare into existence briefly, vanish, and leave no trace, making them nearly impossible to catch in the act. Then there's the quantum twist. Some physicists argue that white holes might emerge from black holes at the end of their life cycles. As a black hole evaporates via Hawking radiation, could its final moments rebound as a white hole, recycling its energy back into the cosmos? This idea, though speculative, offers a poetic symmetry that every collapse could seed a new eruption, a cosmic cycle of destruction and rebirth hidden in the fabric of spacetime. The search for white holes forces us to confront the limits of our understanding. Are they purely mathematical oddities, or do they lurk in the universe's darkest corners, waiting to be discovered? If they're real, they could rewrite the rules of physics, offering gateways to other dimensions or even clues to the origins of the cosmos itself. Until then, white holes remain one of relativity's boldest unfulfilled predictions, a reminder that the universe's greatest mysteries might not be what we see, but what we've yet to imagine. Down at the smallest scales imaginable, far beneath atoms, quarks, even the smallest ripples of energy, spacetime itself might not be smooth and serene, but a seething, turbulent ocean. This is the bizarre realm of quantum foam, a theoretical froth where reality itself bubbles with fleeting particles, microscopic wormholes, and fleeting distortions in the fabric of space and time. Picture the surface of a boiling pot, but instead of water, it's the very foundation of existence, churning with unimaginably tiny fluctuations that pop in and out of existence faster than a blink. If this sounds like science fiction, that's because it skirts the edge of what we can even conceive, yet the math suggests it might be real. The idea of quantum foam emerged from the collision of two titanic theories, quantum mechanics and general relativity. On one hand, quantum mechanics tells us that at the tiniest scales, nothing is ever truly still. Particles flicker into existence, borrowing energy from the vacuum before vanishing again. On the other, relativity describes spacetime as a smooth, bendable fabric. But when you try to merge these ideas, the equations explode into chaos. Space and time themselves seem to break apart into a probabilistic storm, where distances and durations lose all meaning. Quantum foam is the compromise, a way to imagine spacetime not as a calm pond, but as a roiling sea at the Planck scale, where distances are a trillionth of a millimeter. So how do we prove something so infinitesimal exists? The challenge is like trying to photograph the ripples from a single raindrop in a hurricane. Any instrument we build would be too massive, too clumsy to detect such delicate turbulence. But physicists aren't giving up. One approach involves hunting for subtle distortions in light from distant cosmic explosions. If quantum foam is real, photons traveling billions of light years should pick up tiny jitters in their paths, like a ship rocking on a choppy sea. Another wild idea hinges on black holes. Some theories suggest that quantum foam might leave imprints on Hawking radiation, the faint glow escaping a black hole's edge, like finding foam bubbles clinging to a drain. The implications are staggering. If quantum foam is real, it could mean that wormholes, those fabled shortcuts through space-time, might constantly form and collapse at scales too small to see. It might explain why gravity, the last holdout of classical physics, refuses to play nice with quantum theory. And some researchers go even further, suggesting that the foam could be the substrate of reality itself, with particles and forces emerging from its chaos like waves on an ocean. But here's the twist: quantum foam might not just be a curiosity. It could be the key to the universe's deepest secret, a theory of everything. If we can understand how space-time froths at the smallest scales, we might finally bridge the gap between quantum mechanics and gravity, unlocking a unified framework for all of physics. Or it could turn out to be a beautiful dead end, a mathematical mirage that dissolves under closer scrutiny. For now, quantum foam remains one of science's most tantalizing enigmas. It's a reminder that the universe, even at its most fundamental level, is anything but orderly. And if we ever do catch a glimpse of this turbulent underworld, it could reveal a cosmos far stranger, far more dynamic than we ever dared to dream. Until then, we're left peering into the abyss where the fabric of reality itself seems to shimmer with possibilities. High above Earth, hidden in the endless black, conspiracy theorists insist an ancient sentinel watches us, the Black Knight satellite. Stories claim this mysterious object has orbited our planet for 13,000 years, a relic of some long-lost alien civilization silently observing human history unfold. The legend paints a tantalizing picture, an artificial satellite predating human spaceflight by millennia, its origins as inscrutable as its purpose. But here's the twist: despite decades of claims, not a single shred of credible evidence supports its existence. So how did a jumble of space debris and misidentified photographs morph into one of the most enduring extraterrestrial myths of all time? The Black Knight's modern legend began in the 1950s, when newspapers reported that the U.S. Air Force had detected an unknown object in polar orbit. At the height of the Cold War, with Sputnik still fresh in the public's mind, speculation ran wild. Was it a secret Soviet weapon, an alien probe? The truth was far less dramatic. The signals likely came from a combination of natural radio noise and early satellite tracking experiments. Yet the seed was planted. By the 1960s, amateur radio operators claimed to have intercepted strange coded messages from the satellite, fueling rumors of an intelligence behind the transmissions. Then came the images. In 1998, grainy footage from a space shuttle mission appeared to show a dark, irregularly shaped object floating against the curvature of Earth. Conspiracy forums erupted, declaring this the long-sought proof of the Black Knight. But NASA quickly identified it as a thermal blanket lost during a spacewalk, a mundane explanation that did little to dampen the fervor. Later, satellite images of a peculiar debris field near the International Space Station were similarly mislabeled as the mythical object, despite being catalogued space junk. What makes the Black Knight so fascinating isn't just the myth itself, it's the psychology behind its persistence. Humans are pattern-seeking creatures, wired to find meaning in randomness. A tumbling piece of debris becomes an alien artifact. Radio static transforms into an encoded message. In an age where space agencies live stream rocket launches and anyone can track satellites with a smartphone app, the idea that something could remain hidden in plain sight is irresistibly thrilling. The Black Knight taps into deeper anxieties too, the fear that we're not alone, or worse, that we're being watched by forces beyond our understanding. Skeptics argue the legend endures because it's unfalsifiable. Every debunked claim is met with a new layer of speculation. They're covering it up, or you just haven't seen the real evidence. This shifting narrative makes the myth immune to disproof, allowing it to mutate with each retelling. Meanwhile, pop culture cementing the Black Knight in movies, books, and music ensures it remains lodged in the public consciousness. But here's the real irony. Earth's orbit is already crowded with artificial objects, just not alien ones. Over 20,000 pieces of tracked debris circle our planet, from dead satellites to discarded rocket stages. In a way, the Black Knight is a modern-day cargo cult, a myth born from humanity's awe and anxiety about the very real technologies we've launched into the void. Whether as a cautionary tale or a cosmic ghost story, its legacy reveals less about extraterrestrials and more about us, our hunger for mystery, our distrust of authority, and our endless capacity to see monsters in the shadows of the unknown. And as long as the night sky stretches overhead, the legend will likely keep flying, untethered from facts but forever anchored in wonder. Every star in the sky seems solitary, but what if our sun isn't flying solo? Lurking in the frozen darkness beyond Pluto, some astronomers suspect a hidden companion might be stirring up cosmic trouble, a theoretical dwarf star nicknamed Nemesis. This elusive object, if it exists, would follow an absurdly wide orbit, swinging close only once every 26 million years. When it does, its gravity could yank icy comets from the Oort cloud, hurling them toward the inner solar system like a cosmic bowling ball striking pins. The terrifying implication: these icy intruders might explain Earth's periodic mass extinctions, including the asteroid impact that wiped out the dinosaurs. The Nemesis hypothesis emerged in the 1980s when paleontologists noticed a chilling pattern in the fossil record. Major extinction events seem to occur in regular cycles, roughly every 26 to 30 million years. Around the same time, astronomers studying impact craters found similar timing in asteroid strikes. Coincidence seemed unlikely. Something appeared to be triggering these cataclysms like clockwork. Enter Nemesis, the hypothetical Death Star, whose gravitational nudges could send comets careening our way. The math was elegant: a small, cool red dwarf or brown dwarf orbiting up to 1.5 light-years away, so distant it would reflect almost no sunlight, making it nearly invisible to telescopes. But here's where the theory hits turbulence. Despite decades of searching, no trace of Nemesis has been found. Infrared surveys like NAS, a WISE mission, have scanned the skies for faint heat signatures, ruling out any star larger than a brown dwarf within the predicted range. Skeptics argue that the extinction cycle itself might be statistical noise, or that other forces like the solar system's periodic passage through dense galactic regions could perturb comets without invoking a hidden star. Even the name Nemesis reflects the controversy, evoking mythological vengeance rather than scientific detachment. Yet the idea refuses to die. Some researchers suggest Nemesis might not be a star at all, but a rogue planet, a massive world ejected from another system, now drifting at the solar system's edge. Others propose that multiple smaller objects, like the hypothetical Planet 9, could collectively mimic Nemesis's gravitational effects, the most radical twist. Nemesis could have escaped entirely, flung into interstellar space by a passing star long ago, leaving behind only the echoes of its disruptions in our geological record. What makes this cosmic detective story so compelling isn't just the hunt for a missing star, it's what the search reveals about our place in the universe. If Nemesis exists, it would mean our solar system is a binary, rewriting astronomy textbooks. Its absence, though, forces us to confront deeper questions. Are mass extinctions truly cyclical, or do we impose patterns on chaos? Could unseen forces beyond our current understanding still lurk in the dark? Every telescope pointed at the outer solar system isn't just chasing a phantom, it's testing the boundaries of what we consider possible. And whether Nemesis is found or finally laid to rest, the mystery reminds us that even in our own celestial backyard, the universe keeps its most startling secrets close. Spiral galaxies should tear themselves apart. That's the unsettling truth astronomers stumbled upon decades ago when they first mapped how fast stars orbit galactic centers. According to Newton's laws, the outer edges of these swirling cosmic pinwheels should rotate slower than the inner regions, just like planets farther from the sun move more sluggishly. But when scientists measured real galaxies, they got a shock. Stars at the outskirts were whipping around just as fast as those near the core, as if some invisible hand were gripping the galaxy, keeping it from flying apart. This glaring mismatch between prediction and reality became known as the galaxy rotation problem. and it's one of the strongest clues we have that the universe is filled with something we can't see. The simplest explanation, dark matter. If galaxies are embedded in vast halos of this mysterious substance, particles that don't interact with light but exert gravitational pull, their extra mass would explain the star's breakneck speeds. Picture a merry-go-round spinning so fast its riders should go flying, but hidden weights beneath the platform keep everything stable. That's the role dark matter plays in this cosmic dance. Computer simulations back this up. When researchers model galaxy formation with dark matter included, the virtual galaxies rotate just like the real ones. Without it, their stars scatter into the void. But here's where things get complicated. Not everyone is convinced dark matter is the answer. A vocal minority of physicists champion an alternative, modified Newtonian dynamics, or MN. This theory proposes that gravity doesn't behave exactly as Newton or Einstein predicted at extremely low accelerations, like those experienced by stars on galactic fringes. Instead of invoking invisible matter, MN tweaks the equations of gravity itself, suggesting it strengthens slightly where conventional physics says it should fade. In certain galaxies, especially faint, diffuse ones, MN predictions align startlingly well with observations. It's as if the universe has a hidden rulebook for weak gravitational fields, one we've only just begun to decipher. The debate between these two camps isn't just academic, it's a battle for the soul of cosmology. If dark matter is real, we're missing nearly 85% of the universe's mass, a humbling reminder of how little we understand. If MN is correct, we're misunderstanding a force we thought we knew inside out. Both possibilities are equally thrilling, and both face stubborn challenges. Dark matter struggles to explain why some galaxies seem to lack it entirely, like NGC 1052DF2, while MN falters when applied to galaxy clusters or the cosmic web's large-scale structure. New observations keep the mystery alive. The James Webb Space Telescope's razor-sharp infrared vision is revealing baby galaxies in the early universe that rotate too fast for their size, deepening the puzzle. Meanwhile, refined measurements of gravitational lensing how massive objects bend light show distortions that neither dark matter nor MN fully explains. It's becoming clear that the galaxy rotation problem isn't just a single missing piece. It's a symptom of a deeper enigma, one that might require entirely new physics to solve. What makes this puzzle so captivating isn't just the science, it's the stakes. Cracking the rotation mystery wouldn't just settle a decades-old debate. It would redefine our place in the cosmos, revealing whether the universe is dominated by shadowy particles we've yet to detect or governed by laws we've yet to write. Every spiral galaxy, with its stars clinging impossibly tight, is spinning a story far richer than we imagined, and the ending, that's still up for grabs. Empty space isn't empty. That's the first shocking truth behind the vacuum catastrophe, one of the most glaring unsolved problems in physics. According to quantum field theory, the vacuum of space should be a seething, bubbling foam of virtual particles constantly flickering in and out of existence. These quantum fluctuations aren't just theoretical, they've been measured in labs, producing real effects like the Casimir force, where two metal plates in a vacuum inexplicably pull together. But here's the paradox. If you add up all this quantum activity to calculate the energy density of empty space, the result is a number so absurdly large it would have torn the universe apart nanoseconds after the Big Bang. Specifically, the math predicts a vacuum energy density 10 raised to the power of 120 times greater than what we actually observe. That's a 1 followed by 120 zeros, a discrepancy so vast it's like predicting an ocean and finding only a single drop. This chasm between prediction and reality is called the cosmological constant problem, and it cuts to the heart of modern physics. When Einstein first introduced the cosmological constant to balance his equations of general relativity, he called it his greatest blunder. But decades later, astronomers discovered dark energy, the mysterious force accelerating the universe's expansion, and suddenly, the cosmological constant was back in play. The trouble is, the measured value of dark energy's effect is unimaginably tinier than what quantum mechanics suggests it should be. Imagine building a skyscraper designed to withstand a hurricane, only to discover it's holding up against a gentle breeze. The numbers just don't add up, so why doesn't the universe explode? One possibility is that some unknown mechanism cancels out almost all of this vacuum energy, leaving behind the faint whisper we detect as dark energy. Maybe opposing forces or symmetries in quantum fields balance each other with near-perfect precision, like two cosmic waves crashing together to leave barely a ripple. String theorists have proposed landscapes of possible universes, each with different vacuum energies, suggesting we live in one of the rare versions where the numbers are just right for galaxies and life to exist. But this multiverse explanation feels like a mathematical Hail Mary, swapping one mystery for another. Then there's the radical idea that we're missing something fundamental, that quantum field theory and general relativity are both incomplete, and only a theory of quantum gravity can bridge the gap. Perhaps vacuum energy isn't what we think. New theories like entropic gravity or emergent spacetime suggest gravity isn't a fundamental force but a side effect of deeper processes, which could rewrite how we calculate energy densities. Others speculate that dark energy isn't constant but evolves over time, meaning the vacuum catastrophe might be a snapshot of a dynamic process we don't yet understand. The vacuum catastrophe isn't just an abstract puzzle, it's a beacon, illuminating how little we grasp about the fabric of reality. Solving it could unlock everything from the universe's fate to the unification of physics. Until then, the silence of empty space echoes with unanswered questions, reminding us that sometimes nothing is the most complicated thing of all. Imagine floating alone in an infinite void, your entire existence, your memories, your thoughts, even the sensation of having a body, nothing more than a fleeting accident. A random jumble of atoms that, against all odds, arrange themselves into a conscious mind for just a moment before dissolving back into chaos. This is the nightmare scenario of the Boltzmann brain paradox, a thought experiment so unsettling it forces us to question whether anything we perceive as real can be trusted. The paradox starts with a simple premise: given enough time, even the most improbable events become inevitable. In a universe governed by entropy, where disorder reigns supreme, tiny pockets of order can emerge purely by chance. Given eternity, shouldn't the cosmos be teeming with these disembodied observers, popping into existence like bubbles in a boiling pot, only to vanish just as quickly? The deeper you dig, the stranger it gets. If the universe truly is eternal or cyclical, as some cosmological models suggest, the odds of a fully formed, self-aware brain spontaneously assembling from quantum fluctuations become not just possible, but statistically overwhelming. In fact, over infinite time, Boltzmann brains should outnumber ordinary observers like us, beings embedded in stable, structured universes by an unimaginable margin. So why don't they? Why does reality appear so orderly, so persistent, when randomness should dominate? This isn't just a philosophical puzzle. It's a direct challenge to our understanding of probability, cosmology, and even the nature of consciousness itself. One way out of the paradox is to accept that our universe isn't random at all, that some fundamental law or initial condition steers reality away from chaos. This could mean the Big Bang wasn't just another fluctuation, but a singular event with unique properties that set the arrow of time firmly toward order. Inflation theory, with its rapid expansion smoothing out the early universe's wrinkles, offers a possible escape hatch, but even here, problems linger. If other regions of the multiverse experienced different initial conditions, wouldn't most of them still be Boltzmann brain factories? Then there's the radical idea that we might actually be Boltzmann brains. If consciousness is just a fleeting arrangement of particles, how could we ever know? The memories of a past, the sensation of a physical world, all could be illusions conjured by a momentary flicker of order. But this leads to a dizzying contradiction. If all our observations are hallucinations from a random fluctuation, why does science consistently reveal a universe governed by stable, testable laws? The very act of doing science assumes a reality that's coherent and repeatable, not a cosmic dice roll. The Boltzmann brain paradox isn't just an intellectual exercise. It forces us to confront the fragility of our assumptions about existence. Are we the unlikely winners of a cosmic lottery, or is our understanding of probability fundamentally flawed? Could the paradox hint at undiscovered physics that prevents such aberrations, or does it point toward a deeper truth that reality isn't what it seems? Every answer seems to open new questions, leaving us suspended between the profound and the absurd. And in that tension lies the paradox's greatest gift. It reminds us that the universe, for all its apparent order, might still be far stranger than we dare to imagine. Imagine a civilization so advanced they've outgrown planets entirely instead. They build colossal structures around stars, capturing every drop of solar energy to fuel their empire. This isn't just science fiction, it's the essence of the Dyson sphere, a hypothetical megastructure first proposed by physicist Freeman Dyson in 1960. The idea is simple yet staggering: a network of orbiting solar collectors, possibly millions of miles across, enveloping a star to harness its power. While we've never found definitive proof such structures exist, the mere possibility has ignited one of the most thrilling debates in modern astronomy. Where does nature end and alien engineering begin? The search for these cosmic power plants isn't just about spotting unusual starlight patterns. It's a test of imagination, forcing us to rethink how intelligence might manifest across the universe. Take Tabby's star, for instance. Its erratic, deep dimming initially sparked wild speculation about alien megastructures. Though later studies pointed to dust clouds as the likely culprit, the mystery revealed something profound. Our telescopes are now sensitive enough to detect anomalies that, in another era, might have been dismissed as noise. Every oddball star or unexplained infrared signal could, in theory, be a fingerprint of extraterrestrial ambition. But here's the twist: the universe is full of natural phenomena that mimic artificial constructs. Pulsars, quasars, and even rogue planets can produce signals that, to the untrained eye, seem engineered. The challenge lies in distinguishing the truly unnatural from the merely unusual. Some researchers hunt for waste heat, the telltale infrared glow of energy-harvesting civilizations, since even the most efficient Dyson sphere would leak heat into space. Others look for starlight blocked in ways no known astrophysical object could replicate, like geometric shadows or unnatural light curves. The debate isn't just about aliens, it's about pushing science to its limits. Even if every candidate so far has a natural explanation, the pursuit has led to unexpected discoveries. For example, projects scanning for Dyson spheres have uncovered previously unknown types of dust-enshrouded stars and rare cosmic collisions. And the tools developed for this hunt, from advanced machine learning algorithms to ultra-precise light measuring techniques, are now being used to study everything from exoplanets to dark matter. What makes the megastructure hypothesis so compelling isn't just the what if, it's the way it reframes our place in the cosmos. If even one Dyson sphere were found, it would prove that civilizations can outlast their home planets, harnessing stellar energy on scales we can barely comprehend. And if we never find one, the search still expands our understanding of what's possible, blurring the line between astrophysics and archaeology as we sift through starlight for echoes of intelligence. Whether the universe is silent or teeming with builders, the act of looking forces us to confront our own future. After all, if humanity survives long enough, we might someday face the same choice to build our own megastructures or fade into the cosmic dark. Dark energy already pushes the universe apart at an accelerating rate, but what if its grip grows stronger over time? That's the terrifying premise of phantom energy, a hypothetical form of dark energy so potent, it wouldn't just expand the cosmos but eventually shred it apart atom by atom in a cataclysm cosmologists call the Big Rip. Picture this: billions of years from now, galaxies first drift beyond each other's horizons, their light stretched too thin to see. Then, gravity's hold weakens as space itself stretches faster than the speed of light, tearing star systems apart. Planets are ripped from their suns. Finally, in the last horrifying moments, even atomic bonds snap as the fabric of space-time stretches beyond the breaking point. Matter itself dissolves into a sea of disconnected particles, leaving behind a cold, empty void where the universe once was. The math behind this scenario isn't science fiction. It emerges from legitimate solutions to Einstein's equations when dark energy's density increases over time rather than remaining constant. Phantom energy's defining trait is its equation of state, a pressure-to-density ratio less than -1, creating a feedback loop where expansion begets more expansion. The more the universe grows, the stronger phantom energy becomes, accelerating the process until it spirals out of control. It's like a car with a gas pedal stuck to the floor, where every mile only makes the engine roar faster. Yet for all its apocalyptic drama, phantom energy remains speculative. Most observations align with dark energy being a cosmological constant, unchanging and steady. But the mere possibility of phantom behavior lingers because of a glaring gap in our knowledge. We still don't understand what dark energy actually is. Could it evolve? Could it have phases like ice melting into water? The discovery of dark energy's acceleration in the late 1990s was a shock. Phantom energy would upend cosmology entirely. The stakes couldn't be higher. If phantom energy exists, it wouldn't just dictate the universe's fate, it would rewrite the timeline. A big rip could occur in as little as 20 billion years, a cosmic blink compared to the trillions of years projected for a more gradual, heat-death scenario. Some models even suggest subtle signs of phantom behavior could be hiding in current data, like slight discrepancies in supernova brightness or the clustering of galaxies. Future telescopes, like the European Space Agency's Euclid mission, aim to measure dark energy's equation of state with unprecedented precision, hunting for hints of this phantom in the machine. What makes this idea so haunting isn't just the science, it's the philosophical reckoning. A universe that ends in a big rip leaves no legacy, no fossils, not even black holes to mark its passing. It's the ultimate erasure, a finale so absolute it challenges our very notions of meaning in an expanding cosmos. Yet paradoxically, the search for phantom energy also represents science at its most daring, confronting the unthinkable not as prophecy but as possibility. Whether the equations point to oblivion or merely to mathematical curiosity, one thing is clear: the universe's last act may be far stranger than we've ever imagined. If parallel universes exist, hidden realms with their own laws of physics, their own histories, how would we ever know? The multiverse isn't just a sci-fi trope. It's a serious scientific hypothesis, one that could solve one of cosmology's biggest puzzles: why our universe seems so perfectly fine-tuned for life. Tweak the strength of gravity just a fraction, or adjust the mass of an electron by a hair, and stars wouldn't ignite, atoms wouldn't form, and life as we know it would be impossible. The odds of such perfection emerging by chance are astronomically small, unless, of course, there are infinite universes, each with different constants, and we just happen to live in the one where everything clicks. But here's where it gets wild. If other universes are out there, they might not stay neatly separated. Some theories suggest that neighboring universes could bump into one another, leaving behind cosmic bruises, subtle imprints in the fabric of our reality. Imagine two soap bubbles colliding in a sink. The point of contact leaves a faint ripple on each surface. In the same way, a collision with another universe might leave a signature in the cosmic microwave background, the afterglow of the Big Bang. Researchers have scoured the CMB for these telltale patterns, hunting for irregular temperature fluctuations or strange circular anomalies that could betray a multiversal handshake. One tantalizing candidate, the so-called cold spot, has sparked debate. Could this unusually frigid patch of sky be the scar of an ancient collision? Then there's the gravitational echo hypothesis. If parallel universes exist in higher dimensions stacked like pages in a book, their gravity might leak into ours, subtly warping the motion of galaxies or distorting space-time in ways we can't yet explain. Some physicists even speculate that dark matter, the invisible glue holding galaxies together, could be the gravitational shadow of a neighboring universe bleeding into our own. It's a radical idea, but in a field where the unknown dwarfs the known, no possibility can be dismissed outright. The search for multiversal fingerprints is a high-stakes gamble. Unlike most scientific pursuits, where disproving a hypothesis is just as valuable as confirming it, the multiverse is frustratingly slippery. Finding nothing doesn't rule it out. After all, other universes might be forever beyond our reach, their existence forever theoretical. But if we did find evidence, it would be the most profound discovery in history, proving that reality is vaster, stranger, and more interconnected than we ever dreamed. Until then, the multiverse remains the ultimate cosmic tease, a possibility so compelling it reshapes how we see our place in the cosmos, yet so elusive it might always hover just beyond the edge of proof. Whether it's real or not, the idea alone stretches our imagination, forcing us to confront the deepest question of all. In an infinite sea of possibilities, what else might be out there waiting to be found? In the world of quantum physics, where the impossible often becomes reality, time crystals stand out as one of the most mind-bending discoveries of the 21st century. Unlike ordinary crystals like diamonds or snowflakes, which repeat their atomic patterns in space, time crystals repeat their structure in time, flipping between states in a never-ending cycle without any energy input. Imagine a clock that ticks forever without winding, or a dance where the steps repeat perfectly without the dancers ever tiring. That's the essence of a time crystal, a structure that breaks the symmetry of time itself, defying the classical laws of thermodynamics that say all systems must eventually settle into equilibrium. The idea was first proposed in 2012 by Nobel laureate Frank Wilczek, who wondered if a quantum system could exhibit perpetual motion without violating the laws of physics. At first, many dismissed it as theoretical fantasy. After all, perpetual motion machines are supposed to be impossible. But just 5 years later, two separate teams of scientists brought time crystals to life in labs, using chains of ions or diamond defects to create systems that oscillated between states indefinitely, driven not by energy but by quantum coherence. It was like discovering a new state of matter, one where time itself becomes part of the crystal's architecture. What makes these structures so revolutionary isn't just their defiance of thermodynamics, it's the doors they could open. Time crystals might exist naturally in extreme cosmic environments, like the crushing depths of neutron stars or the chaotic aftermath of the Big Bang. Some theorists speculate they could even form in the ultra-cold, low-energy corners of space where quantum effects dominate. If so, they'd be invisible to traditional telescopes, their rhythmic pulses detectable only through subtle gravitational waves or anomalies in particle behavior. Then there's the technological potential. Time crystals could revolutionize quantum computing by acting as ultra-stable memory for qubits, immune to the decoherence that plagues current systems. They might even pave the way for entirely new forms of energy storage, where information or motion is preserved indefinitely without degradation. The catch: we're still in the earliest stages of understanding how to harness them. Lab-made time crystals are fragile, requiring near absolute zero temperatures and precise magnetic fields to survive. Scaling them up for practical use is like trying to build a skyscraper out of soap bubbles, possible in theory, but fraught with challenges. The real enigma lies in what time crystals imply about the fabric of reality. If matter can oscillate endlessly without energy, does that mean the universe has loopholes we've yet to exploit? Could they hint at hidden symmetries in time itself, or even a deeper connection between quantum mechanics and the arrow of time? Every experiment peels back another layer, revealing a world where the lines between science and science fiction blur. And as researchers probe further, one thing becomes clear: time crystals aren't just a curiosity, they're a gateway to a stranger, more dynamic universe than we ever imagined. Somewhere beyond the edge of everything we can see, something unimaginably vast may be pulling at our universe like a cosmic magnet. This is the eerie phenomenon astronomers call dark flow, the discovery that hundreds of galaxy clusters are drifting in the same direction at staggering speeds of over 2 million miles per hour, as if caught in a river of space-time flowing toward an unseen destination. The strangest part, this motion defies everything we know about cosmic expansion, where galaxies should be scattering evenly in all directions like debris from an explosion. Instead, these clusters move with eerie coordination, suggesting our universe isn't just expanding, it might also be sliding. The clues first emerged in 2008, when astronomers studying the cosmic microwave background noticed something peculiar. The afterglow of the Big Bang showed subtle distortions in the direction of the constellations Centaurus and Hydra, as if photons from the early universe had been nudged by the gravity of something massive beyond our observational horizon. Follow-up studies using X-ray telescopes revealed galaxy clusters along this path weren't just drifting. They were racing, their motion too uniform and too fast to be explained by the gravitational pull of any known structure. Even the Great Attractor, that mysterious concentration of mass pulling nearby galaxies, couldn't account for the scale of this motion. The flow extended over billions of light years, encompassing clusters that shouldn't be able to influence each other. It was as if the universe itself had a tilt, a secret current flowing through the void. So what could possibly exert such force? One radical idea points to other universes. If our cosmos is part of a multiverse, a frothing sea of bubble universes born from eternal inflation, then a neighboring universe might lie just beyond our observational limits, its gravity leaking into ours like a shadow through a curtain. The sheer mass required to tug entire galaxy clusters would be incomprehensible, perhaps a cosmic sibling orders of magnitude larger than our own universe. Alternatively, dark flow might hint at exotic physics, a flaw in Einstein's relativity, a previously unknown property of dark energy, or even relics from before the Big Bang, like scars from a collision with another spacetime. Skeptics argue the anomaly could be a measurement error or a statistical fluke. After all, tracing galaxy motions across such vast distances is like trying to map ocean currents by watching scattered leaves. But the data persists, with newer surveys like the E-Rosetta X-ray telescope confirming the pattern. If dark flow is real, the implications rewrite cosmology. It would mean our universe isn't just influenced by what's inside it, it's beholden to forces from beyond the edge of existence. A reminder that the cosmos might be far grander and far stranger than we ever dared to dream. The hunt for answers continues, with telescopes probing deeper into the flow's origin. Whether it reveals a multiversal neighbor or a new law of physics, one thing is certain: the universe never stops surprising us. And in that uncertainty lies the thrill of discovery, the chance that somewhere in the darkness, the next great cosmic secret is waiting, pulling us toward the unknown. For over a century, physics has been split down the middle by two monumental theories, each breathtakingly accurate in its own domain, yet utterly incompatible when forced to share the same stage. On one side stands Einstein's general relativity, which paints gravity as the curvature of spacetime, a smooth geometric dance where planets and black holes move according to the bends in the cosmic fabric. On the other side is quantum mechanics, which reveals a subatomic world of frenzied probabilities, where particles flicker in and out of existence and nothing is certain until it's observed. Both frameworks have been tested to staggering precision. Relativity predicts the orbit of Mercury and the bending of starlight, while quantum mechanics underpins everything from smartphones to supercomputers. Yet when you try to merge them, the equations explode into nonsense. At the heart of a black hole or the moment of the Big Bang, where both gravity and quantum effects dominate, the math simply breaks. This is the quantum gravity conundrum, and solving it might be the key to unlocking reality's deepest layers. The quest for quantum gravity isn't just academic, it's a race to answer questions that define the universe. What happens at the center of a black hole where matter is crushed to infinite density? What sparked the Big Bang? Even the nature of time itself might shift if we crack this puzzle. The leading contenders for a unified theory sound like they are ripped from science fiction. String theory proposes that the fundamental building blocks of reality aren't particles but tiny, vibrating strings with different harmonies corresponding to different forces. It elegantly merges gravity with quantum mechanics but demands extra dimensions, possibly 10 or more, curled up too small for us to see. Then there's loop quantum gravity, which imagines space-time as a web of interconnected loops, a pixelated structure that becomes apparent only at the tiniest scales. Unlike strings, loops don't require extra dimensions, but they struggle to explain how smooth space-time emerges from this granularity. Other approaches are even more radical. Causal dynamical triangulation suggests space-time assembles itself from geometric building blocks, like a cosmic Lego set. Entropic gravity argues gravity isn't a fundamental force at all but an emergent effect of entropy, a cosmic illusion born from the universe's tendency toward disorder. And then there's the holographic principle, which posits that all the information in a volume of space can be encoded on its boundary, like a 3D movie projected from a 2D screen. These ideas aren't just abstract musings, they're backed by serious math and have real consequences. If spacetime is truly pixelated, for instance, it would mean there's a fundamental limit to how precisely we can measure anything, a cosmic resolution beyond which reality gets blurry. Yet for all their ingenuity, these theories share one frustrating trait: a lack of experimental proof. Testing quantum gravity requires energies so extreme they dwarf anything our particle colliders can produce. Some researchers hunt for indirect clues, subtle anomalies in gravitational waves, or faint signatures in the cosmic microwave background that might betray space-time's granularity. Others look for deviations in the behavior of ultra-dense neutron stars where gravity and quantum forces collide. There's even hope that black holes, those ultimate cosmic laboratories, might leak secrets through their Hawking radiation. But until we find hard evidence, quantum gravity remains a frontier of pure imagination, where mathematicians and physicists play with equations like explorers sketching maps of undiscovered lands. What makes this search so electrifying isn't just the promise of a unified theory, it's the possibility that in bridging these two worlds, we might stumble upon something entirely unexpected. Perhaps gravity and quantum mechanics aren't just incompatible because we're missing a piece, but because our very notions of space, time, and causality need reinventing. Every failed experiment, every dead end, is a reminder that the universe doesn't owe us answers that fit neatly into human logic. And if history is any guide, the ultimate solution won't just reconcile relativity and quantum mechanics, it will rewrite the rules entirely, revealing a cosmos stranger than we've ever dared to dream. Every second, trillions of ghostly particles pass through your body without you ever noticing neutrinos, the universe's most elusive cosmic messengers. But these aren't just any neutrinos. Billions of years ago, when the universe was less than 2 seconds old, a flood of low-energy neutrinos broke free from the primordial soup of particles, racing outward in all directions. Today, these ancient relics still permeate every corner of space, forming what scientists call the cosmic neutrino background, a faint echo of the Big Bang that's even older than the cosmic microwave background. Detecting these whisper-thin particles could unlock secrets from the universe's first moments, offering a glimpse into a time before stars, before galaxies, before even light could travel freely. The challenge: neutrinos barely interact with matter. They're often called ghost particles because they can sail through entire planets as if they weren't there. The cosmic neutrino background is even trickier to spot. These neutrinos have been stretched by the expanding universe to ultra-low energies, making them 1 billion times fainter than those produced by the sun or supernova. Traditional detectors, like the giant tanks of water buried deep underground that catch higher energy neutrinos, are useless here. These primordial neutrinos slip through like shadows through a sieve. Yet the payoff for catching them would rewrite cosmology. Unlike photons from the cosmic microwave background, which were set free 380,000 years after the Big Bang, neutrinos decoupled just 1 second after creation, when the universe was a seething plasma of quarks and gluons. If we could measure their energy distribution, we'd essentially have a snapshot of the cosmos in its infancy, revealing conditions during an era no telescope can peer into directly. Some theories suggest these neutrinos might even carry imprints of cosmic inflation, that explosive expansion thought to have shaped the universe's large-scale structure. Others speculate they could hint at undiscovered particles or forces that existed only in those first fleeting moments. The hunt is already pushing technology to its limits. Proposed experiments aim to capture the cosmic neutrino background by looking for rare collisions with radioactive isotopes or using ultra-sensitive quantum sensors that could detect the minuscule momentum transferred when a neutrino grazes an atom. It's like trying to hear the faintest whisper in a hurricane, but if we succeed, the whispers could tell us how the universe grew from a microscopic speck to everything we see today. What makes this search so thrilling isn't just the technical audacity, it's the sheer scale of time we're bridging. These neutrinos have been traveling since the first tick of the cosmic clock, undisturbed by stars, black holes, or galaxies. They're pristine messengers from a time before time had meaning, carrying secrets we're only now learning how to decode. And if we can finally catch them, it won't just be a discovery, it'll be a conversation with the universe itself, spoken in a language older than light. Imagine stepping into a room filled with mirrors, where every reflection seems real until you reach out and touch the glass. Now take that illusion and scale it up to cosmic proportions. That's the essence of the holographic principle, a theory so radical it suggests everything we perceive as reality might be nothing more than a shadow cast from the edges of the universe. This mind-bending idea emerged from the study of black holes, where physicists discovered something startling. All the information about objects swallowed by a black hole isn't lost inside its crushing depth. It's somehow encoded on its event horizon, the point of no return. If that's true for black holes, could the entire universe work the same way? Are we and everything around us just a three-dimensional projection of data written on some distant two-dimensional surface? The math behind this principle is as elegant as it is strange. Just as a hologram stores a 3D image on a flat film, the universe might encode its entire contents, every star, every planet, every thought, on a boundary we can't see or touch. This isn't just a poetic metaphor. String theorists have shown that the equations describing certain higher dimensional universes can be perfectly translated into lower dimensional ones without losing any information. It's like rewriting an entire library of books into the margins of a single page, yet somehow preserving every word. The holographic principle takes this further, suggesting that space itself isn't fundamental but emergent, a byproduct of quantum information interacting at the universe's edges. But how could something so abstract ever be tested? One clue lies in the fabric of spacetime itself. If reality is pixelated, built from tiny, indivisible units of information, then there should be a fundamental limit to how precisely we can measure anything, a cosmic resolution beyond which details blur. Experiments like the holometer at Fermilab have hunted for this graininess by firing lasers down long tunnels, searching for minuscule jitters in their paths that might betray spacetime's hidden structure. So far, the results have been inconclusive, but the hunt isn't over. Future gravitational wave detectors, sensitive enough to catch ripples from the earliest moments of the Big Bang, might finally spot the holographic noise woven into the universe's foundations. What makes this idea so revolutionary isn't just the science, it's the philosophical earthquake it unleashes. If the holographic principle holds, then free will, consciousness, even the passage of time could be secondary phenomena, illusions generated by deeper processes we're only beginning to grasp. It's a humbling thought that the solidity of the world around us, the very sense that we're here at all, might be a kind of cosmic sleight of hand. Yet for all its strangeness, the principle offers hope too, a potential bridge between quantum mechanics and gravity, two languages of physics that have refused to speak to one another for a century. Whether the universe is truly a hologram remains an open question, but the pursuit itself has already reshaped how we see reality. Every experiment, every calculation, peels back another layer, revealing a cosmos far more interconnected and far more mysterious than we ever imagined. And if one day we find proof that we're living in a projected world, it won't diminish the wonder, it'll only deepen it, showing that even the simplest truths can hide universes within universes, waiting to be decoded. Magnets are everywhere, sticking notes to your fridge, guiding compass needles north, even humming inside your headphones. But there's something peculiar about them. Every magnet we've ever found, no matter how small or powerful, has two poles. A north and a south break a magnet in half, and you don't isolate a single pole. You get two new magnets, each with its own pair of poles. This seems like an unbreakable rule of nature until you dive into the equations of quantum physics, where a tantalizing possibility emerges. Hidden in the math is a prediction so radical it could rewrite textbooks: the existence of magnetic monopoles, particles with just one pole, a north without a south, or vice versa. These hypothetical entities aren't just curiosities, they could be the missing key to unifying the fundamental forces of the universe. The hunt for monopoles began in the mind of Paul Dirac, the visionary physicist who first theorized their existence in 1931. Dirac showed that if even a single magnetic monopole existed somewhere in the cosmos, it would explain why electric charge comes in discrete, indivisible units, a fact that had baffled scientists for decades. But the implications go far deeper. Grand unified theories, which attempt to merge the electromagnetic, weak, and strong nuclear forces into a single framework, predict that monopoles should have been produced in staggering numbers during the universe's first split second after the Big Bang. These primordial relics would be cosmic heavyweights, with masses a trillion times heavier than a proton, and their discovery would offer direct proof that the forces we see today were once united as one. Yet after nearly a century of searching, not a single confirmed monopole has been found. Detectors buried deep underground, shielded from cosmic rays, have listened for the telltale ionization trails these particles would leave as they plowed through matter. Balloon-borne experiments have scoured the upper atmosphere for traces. Even ancient minerals, which could have recorded the passage of monopoles over geological timescales, have been examined for clues. The silence is deafening. This absence isn't just a minor hiccup, it's a crisis for some of physics' most ambitious theories. If monopoles were created in the early universe as predicted, why didn't they persist in detectable numbers? One possibility is that cosmic inflation, the universe's explosive expansion in its first fraction of a second, stretched spacetime so dramatically that monopoles were diluted to near non-existence, scattered so thinly that finding one would be like spotting a single grain of sand in a desert the size of the observable universe. Others speculate that monopoles might be hiding in cosmic strings, hypothetical defects in spacetime left over from the early universe's phase transitions. These ultra-thin, ultra-dense filaments could have trapped monopoles like bugs in amber, preserving them in regions we've yet to explore. Then there's the more unsettling option that our theories are wrong. Perhaps grand unification doesn't happen the way we think, or maybe monopoles decayed into other particles long ago. The absence of monopoles might be a clue that the universe took a different path in its infancy, one we're only beginning to piece together. What makes the monopole quest so compelling isn't just the science, it's the lesson it teaches about exploration. Sometimes, the universe's most profound secrets aren't revealed by what we find, but by what we don't. Every empty detector, every silent experiment, forces us to question, refine, and sometimes revolutionize our understanding. And if a monopole is ever discovered, whether in a lab, a chunk of moon rock, or the depths of space, it won't just be a new particle. It'll be a message from the universe's first moments, a whisper from a time when the laws of physics were nothing like we know today. Until then, the search continues, a testament to human curiosity and the enduring mystery of the cosmos. Crossing the event horizon of a black hole should be the ultimate cosmic leap of faith, a one-way trip where gravity's grip becomes inescapable. Yet according to Einstein's general relativity, you wouldn't feel anything unusual in that fatal moment. Space and time might warp beyond recognition, but the laws of physics assure a smooth, if doomed, descent. But here's where quantum mechanics crashes the party with a fiery twist. At the quantum level, the event horizon might not be a silent threshold at all. Instead, it could be a raging inferno, a firewall of high-energy particles that would vaporize anything daring enough to approach. This isn't science fiction. It's a genuine paradox that's been tearing physicists apart for over a decade, forcing them to question whether information, space-time, or even black holes themselves work the way we think they do. The firewall idea erupted onto the scene in 2012, when a group of researchers realized something startling about black holes and quantum entanglement. Normally, entanglement, the spooky link between particles that instantly mirrors changes across any distance, is a delicate phenomenon. But at the event horizon, particles become entangled in conflicting ways, creating a quantum impossibility. The only escape from this mathematical trap, a catastrophic breakdown of the vacuum, producing a searing wall of energy that would annihilate any infalling object. It's like stepping onto what you thought was a tranquil beach, only to find it's actually the surface of the sun. The implications are staggering. If firewalls exist, Einstein's prediction that you'd float past the horizon unharmed, a cornerstone of general relativity, is dead wrong. Yet the paradox runs deeper than just two theories disagreeing. At its heart is the black hole information paradox, Stephen Hawking's famous puzzle about whether information swallowed by a black hole is truly lost forever. Quantum mechanics forbids such erasure, insisting information must be preserved, even if scrambled beyond recognition. Firewalls emerged as a brutal solution. If information can't be destroyed, maybe it's forcibly encoded in the thermal radiation at the horizon, burning incoming matter to ash in the process. But this raises new questions. If the horizon is lethal, what happens to the no-drama principle of relativity? And how does the black hole's interior, the mysterious realm beyond the horizon, even exist if nothing can cross intact? The debate has spawned wild alternatives. Some theorists propose that black holes have no interiors at all, that what we perceive as a singularity is actually a two-dimensional surface, holographically encoding all the information of infalling objects. Others suggest the firewall isn't a permanent feature but a fleeting burst, like the shock wave from a sonic boom, triggered only when the black hole is disturbed. Then there's the even more radical idea that spacetime itself is fundamentally unstable near the horizon, fracturing into a foam of quantum bubbles that make concepts like inside and outside meaningless. What makes this paradox so electrifying isn't just the clash of theories, it's the experimental stakes. If firewalls are real, advanced civilizations or future humans might detect their gamma-ray signatures. Gravitational wave observatories could hunt for echoes in black hole mergers, subtle ripples betraying the firewall's presence. Even lab experiments with analogs of black holes, using sound waves or light in specially engineered materials, might simulate horizon physics to test these ideas. But perhaps the greatest lesson of the firewall paradox is how little we truly understand about gravity's extremes. Black holes were once thought to be simple, just mass, spin, and charge. Now they're the ultimate proving grounds for physics, where quantum weirdness and cosmic forces collide in ways that defy intuition. Whether the firewall stands or falls, one thing's certain: the universe's darkest secrets aren't hidden in the black hole's depths, but dancing at its edge, where reality itself seems to flicker between destruction and revelation. What if everything you've ever known, the stars, the laws of physics, even the sensation of wind on your skin, was nothing more than lines of code in an unfathomably advanced simulation? This is the unsettling premise of the simulation hypothesis, a theory that suggests our entire universe might be an artificial construct designed by a civilization with technology so sophisticated their simulations are indistinguishable from reality. At first glance, it sounds like the plot of a sci-fi movie, but the idea has gained traction among philosophers, physicists, and even tech billionaires, not because there's evidence, but because it's shockingly hard to disprove. The argument hinges on probability. If future civilizations develop the power to create hyper-realistic simulations populated by conscious beings, they might run countless iterations, each containing universes with inhabitants who believe they're real. Statistically, the odds of us being in the original, base reality dwindle to near zero. It's like realizing you're probably not the first person to shuffle a deck of cards, but the 10 trillionth. The chances of uniqueness are vanishingly small. This logic, famously championed by philosopher Nick Bostrom, doesn't prove we're in a simulation, but it does force a humbling question. If it's possible, how would we ever know? The real twist is that the simulation hypothesis, by its very design, might be untestable. A perfect simulation would bake its own rules into every aspect of reality, leaving no obvious glitches. But what if the simulation isn't perfect? Some theorists suggest hunting for cosmic shortcuts, places where the programmers might have cut corners to conserve computational power. For instance, if the universe is rendered only when observed, like a video game loading textures as you approach, we might find anomalies in the behavior of quantum particles or inconsistencies in the fine structure constant, a fundamental value governing electromagnetism. Others propose that high-energy cosmic rays could reveal pixelation in spacetime if the universe operates on a finite quantum grid. Yet even if we found such glitches, the debate wouldn't end. A simulation sophisticated enough to create conscious beings would likely anticipate and correct for these hiccups, or even embed them intentionally as Easter eggs. The hypothesis also spirals into infinite regression. If we're simulations, could our simulators themselves be simulations ad infinitum? And if reality is layers deep, does the concept of real lose meaning altogether? Beyond the technical puzzles, the simulation hypothesis forces a philosophical reckoning. If we can't prove we're not in a simulation, does it change how we live? Some argue it shouldn't, whether the universe is coded or cosmic. Our experiences and emotions remain equally vivid. Others see it as a call to hack the system, searching for exploits or ways to communicate with our hypothetical creators. Elon Musk has quipped that the odds we're in base reality are 1 in billions, while physicist Neil deGrasse Tyson counters that the simulators would likely quarantine us like a corrupted file, making contact impossible. What makes this idea so gripping isn't its plausibility, but its ability to dissolve the boundary between science and metaphysics. It challenges the limits of empiricism, asking whether some truths might lie forever beyond the reach of experimentation. And in doing so, it mirrors humanity's oldest existential questions, just dressed in the language of quantum computing and artificial intelligence. Whether the universe is a simulation or not, the hypothesis's real power lies in its ability to make us wonder with fresh eyes what reality actually is. And that in itself might be the point. Time travel isn't just a fantasy, it's a mathematical possibility hidden in Einstein's equations. Wormholes, cosmic strings, and black holes all offer potential pathways to the past, bending spacetime into loops where cause and effect could twist into knots. But Stephen Hawking, ever the skeptic, put forward a tantalizing idea. What if the universe itself has a built-in safety mechanism, a cosmic kill switch that prevents paradoxes before they can unravel reality? This is the chronology protection conjecture, a theory that suggests time travel to the past isn't just impractical, it might be fundamentally forbidden by the laws of physics. At its core, the conjecture is a bet against chaos. Hawking noticed something peculiar about the math behind time loops. Every scenario that allowed backward time travel also introduced catastrophic instabilities. Imagine a single photon traveling back in time, hitting its past self, and amplifying its own energy in an endless feedback loop. In theory, this could create a self-sustaining explosion of infinite energy, a paradox so violent it would rip space-time apart at the seams. Nature, Hawking argued, likely abhors such absurdities as much as it abhors a vacuum. Just as quantum mechanics prevents electrons from crashing into atomic nuclei, some undiscovered law might prevent time travelers from rewriting history. But here's where it gets even stranger. The conjecture isn't just about grandmother paradoxes or killing Hitler. It's about the fragility of physics itself. General relativity allows for closed time-like curves, paths through spacetime that loop back on themselves. Yet every time scientists explore these solutions, quantum effects seem to sabotage them. Virtual particles, those fleeting quantum fluctuations, could pile up at the threshold of a time machine, their collective energy distorting spacetime just enough to collapse the passage. It's as if the universe has a failsafe, a way to police its own rules before they're broken. The real mystery lies in whether chronology protection is a fundamental law or merely a placeholder for deeper physics we don't yet understand. Some theorists propose that quantum gravity, the still elusive theory bridging relativity and quantum mechanics, might hold the answer. If spacetime is granular at the smallest scales, more like a mesh than a smooth fabric, those tiny pixels could stiffen under time travel conditions, snapping any would-be paradoxes like a taut thread. Others suggest that the multiverse could offer an escape hatch. Instead of preventing time travel, maybe the universe splits into parallel timelines whenever a paradox looms, preserving causality by branching reality itself. Hawking himself admitted the conjecture was more intuition than ironclad proof. After all, absence of evidence isn't evidence of absence. Just because we haven't met time tourists doesn't mean they're impossible. Future discoveries might reveal loopholes like exotic matter with negative energy that could stabilize wormholes without triggering spacetime's defenses. Or perhaps we'll find that chronology protection isn't absolute, but probabilistic, like a cosmic game of Russian roulette where most trigger pulls result in safety, but every so often reality loses. What makes this idea so mesmerizing isn't just the science, it's the philosophical weight. If Hawking was right, the universe isn't just a stage for events. It's an active referee, enforcing rules we're only beginning to glimpse. Time's arrow might not just be a feature of entropy but a cosmic commandment, woven into the fabric of existence. And until we crack the code of quantum gravity or stumble upon a time machine's blueprints, the conjecture stands as both a warning and a challenge. The past might be locked away not by chance but by design. Black holes have long been the ultimate cosmic in points regions of infinite density where gravity wins so completely that not even light can escape. But what if that's not the full story? Beneath the event horizon, where classical physics breaks down, quantum mechanics might be rewriting the rules in the most spectacular way possible. Enter Planck stars a radical idea that dares to suggest black holes don't end in singularities at all. Instead, at the very core of these gravitational monsters, quantum effects could slam the brakes on collapse, compressing matter into a sphere no larger than a grain of sand but with the mass of a star. This isn't just a tiny tweak to black hole theory, it's a complete overhaul, turning the universe's most destructive objects into cosmic phoenixes, hiding the seeds of rebirth within their crushing depths. The magic lies in quantum gravity's resistance to infinities. According to general relativity, a black hole's core collapses endlessly, reaching a point where density becomes infinite and spacetime curves beyond repair. But infinities are nature's red flags. They usually signal where our theories fail. Loop quantum gravity, one of the leading candidates to unify quantum mechanics and relativity, proposes a solution. At the Planck scale, space-time isn't smooth and continuous but granular, like a digital image made of tiny pixels. When matter in a black hole reaches this scale, it doesn't collapse further, it rebounds. Imagine squeezing a spring to its absolute limit. The harder you press, the fiercer it pushes back. That rebound could transform the singularity into a Planck star, a fleeting, ultra-dense object where gravity and quantum forces duel to a standstill. Here's where it gets even wilder. A Planck star wouldn't just sit quietly at a black hole's heart. It might eventually explode. The rebound's energy, trapped for eons by the black hole's gravity, could burst free as the star's surface nears the event horizon. To an outside observer, this would look like a white hole, a black hole running in reverse, violently ejecting all the matter it once swallowed. The catch: time dilation near a black hole's edge is so extreme that what feels like milliseconds inside could equate to billions of years passing in the outside universe. That means a Planck star formed in the early cosmos might only now be detonating, lighting up the sky as a sudden, unexplained burst of energy. Could some of the mysterious high-energy cosmic flares we've detected actually be the dying screams of these ancient quantum anomalies? The implications ripple far beyond black hole interiors. If Planck stars exist, they'd offer an elegant fix to the black hole information paradox. The puzzle of whether matter swallowed by black holes is lost forever. Instead of vanishing into a singularity, information could be preserved in the Planck star's structure, then scattered back into the universe during its explosive finale. It's a cosmic recycling program on the grandest scale, where nothing is truly destroyed, only transformed. Of course, the theory is speculative. No telescope has ever glimpsed a Planck star's eruption, and the energies involved push the limits of what we can simulate or observe. But that's what makes this idea so thrilling. It's a reminder that even the darkest corners of the universe might hide surprises, waiting for us to rethink our assumptions. Whether Planck stars are real or not, they challenge us to imagine a cosmos where death isn't eternal, where even the void has a heartbeat, and where the universe's most terrifying monsters might just be sleeping giants, biding their time until they bloom anew. The Big Bang isn't the only creation story science has to offer. Imagine instead a cosmos without a singular beginning, no explosion from nothingness, no unfathomable singularity. Instead, picture two vast, parallel sheets of reality floating in a higher dimensional space, drifting closer until they collide with cataclysmic force. This is the essence of the Ekpyrotic Universe, a radical alternative to the Big Bang that swaps cosmic birth for cosmic collision. The name comes from the Greek word for conflagration, and it's a fitting label for a theory that reshapes not just how the universe began, but how it might cycle through endless rebirths. At the heart of this idea are brains, short for membranes, a concept borrowed from string theory. These aren't just abstract mathematical constructs, they're dynamic, multidimensional surfaces that could stretch across entire universes. In the ekpyrotic scenario, our universe exists on one such brain, separated from another by a sliver of higher dimensional space-time. When these brains collide, the energy released doesn't just spark stars and galaxies, it births an entire cosmos. The kicker: this process might repeat indefinitely, with brains oscillating in an endless dance of destruction and creation. No singularities, no mysterious before the Big Bang, just an infinite cycle of cosmic renewal. What makes this model so compelling is how neatly it sidesteps some of the Big Bang's thorniest puzzles. Inflation, the rapid expansion thought to smooth out the early universe's wrinkles, happens naturally as the brains rebound from collision. The universe's eerie uniformity, its temperature nearly identical in all directions. isn't a coincidence but a consequence of the brain's slow, steady approach before impact. Even dark energy, the mysterious force accelerating cosmic expansion, could be a shadow of the brain's gravitational tug in higher dimensions. It's as if the Ekpyrotic Universe takes the patchwork fixes of standard cosmology and weaves them into a single, elegant tapestry. Yet for all its theoretical beauty, the Ekpyrotic model remains speculative. No experiment has yet detected evidence of higher dimensions or colliding brains. Critics argue that the scenario requires impossibly fine-tuned conditions. The brains must align with near-perfect symmetry to avoid a chaotic, uninhabitable universe. And while the theory predicts subtle signatures in the cosmic microwave background, like distinctive swirls in polarization patterns, these haven't been conclusively observed. Still, the mere possibility challenges us to rethink cosmology's sacred cows. If the Big Bang was just one page in an infinite cosmic saga, what other surprises might the universe be hiding? The Ekpyrotic Universe isn't just a scientific hypothesis, it's a philosophical provocation. It dares us to question whether the universe's origins are truly unknowable or simply waiting for the right perspective. And in a cosmos where dark matter eludes detection and quantum particles defy logic, perhaps the wildest ideas are the ones we can't afford to ignore. Whether this cyclical vision holds up or fades into the annals of fringe theories, it stands as a testament to human imagination's power to rewrite the cosmos's oldest story. After all, if the universe can reinvent itself, why can't we? Neutrinos are the ultimate cosmic shape-shifters, particles so elusive they can pass through light years of lead without a single interaction, yet so abundant that trillions stream through your body every second. But their most baffling trick isn't their stealth, it's their ability to transform mid-flight. Imagine a strawberry turning into a blueberry, then a raspberry, all while zipping through space at nearly the speed of light. This bizarre phenomenon, called neutrino oscillation, upended decades of scientific consensus. Initially dismissed as massless phantoms obeying the Standard Model's strict rules, neutrinos were caught red-handed in the late 90s, changing flavors electron, muon, and tau as they traveled. The implications were staggering. If neutrinos oscillate, they must have mass. And if they have mass, our understanding of the universe just got a lot more complicated. The mystery deepens when you ask how much mass. Neutrinos are absurdly lightweight, at least 10 million times lighter than electrons, the next lightest particles. Why such a gap? One theory points to a cosmic seesaw. Ultra-heavy hypothetical particles, far beyond what our colliders can detect, might exist in symmetry with neutrinos, dragging their masses down to nearly zero through a mechanism called the seesaw model. It's as if the universe placed neutrinos on a gravitational diet, leaving them barely tipping the scales. But there's a tantalizing twist. This process could also explain why matter dominates over antimatter in the cosmos. During the seesaw's balancing act, neutrinos might have triggered a slight preference for matter in the early universe's chaos, tilting the scales just enough to leave us with galaxies, stars, and planets instead of an empty void. Yet the plot thickens when experiments like Japan's Super Kamiok and the ice cube detector in Antarctica reveal another oddity. Neutrinos and antineutrinos oscillate differently. This asymmetry, known as CP violation, is like finding out a coin toss isn't fair. It lands heads more often than tails. If neutrinos break this symmetry more dramatically than quarks do, they could be the architects of our matter-rich universe. The problem: current measurements show neutrino CP violation is frustratingly faint, leaving scientists scrambling to refine their detectors. Future projects like the Deep Underground Neutrino Experiment do aim to amplify these signals, hunting for discrepancies so subtle they'd make a quantum physicist sweat. But here's the real kicker. Neutrinos might be messengers from beyond the standard model. Their feather-light masses hint at undiscovered forces or extra dimensions. Perhaps they're the only particles sensitive enough to feel gravity's quantum whispers. Some theories even suggest neutrinos are Majorana particles, meaning they're their own antimatter counterparts. If true, this would rewrite particle physics rulebook, offering a pathway to unification theories that tie together all fundamental forces. The challenge, proving it requires catching neutrinos in the act of a vanishingly rare decay process. A feat so difficult it's been compared to listening for a single cough in a stadium during a rocket launch. What makes neutrinos so electrifying isn't just their scientific defiance, it's their humility. They're the universe's quietest rebels, slipping through detectors unnoticed while holding answers to its grandest questions. Every oscillation, every faint interaction is a clue etched in quantum ink, waiting for us to decipher. And as we peer deeper into their shadows, we're not just studying particles, we're reading the hidden diary of the cosmos, one ghostly flicker at a time. Somewhere in the depths of space, nature is hurling particles at Earth with energies so extreme they defy belief. Cosmic rays, packing a punch millions of times more powerful than anything humanity's most advanced atom smashers can produce. These aren't just ordinary particles, they're ultra-high-energy cosmic rays, atomic nuclei screaming through the void at nearly the speed of light, each carrying the kinetic equivalent of a well-thrown baseball compressed into a single subatomic projectile. When one of these microscopic bullets slams into Earth's atmosphere, it triggers a cascade of secondary particles so vast it can light up detectors across dozens of square miles. The real shocker, we still have no idea what cosmic cataclysms are capable of launching them. The scale of this mystery becomes clear when you realize these particles shouldn't exist, at least not according to conventional physics. Known as the GZK limit, a theoretical barrier proposed by Greisen, Zatsepin, and Kuzmin in the 1960s, predicts that ultra-high-energy cosmic rays traveling across intergalactic space should lose energy over long distances as they collide with the cosmic microwave background. Yet here they are, arriving with energies that blast right through this ceiling. It's like finding arrows embedded in a castle wall with such force that they'd require a bow no human could possibly draw. So where's the archer? One leading suspect is active galactic nuclei, supermassive black holes at the hearts of distant galaxies, devouring matter and spewing jets of plasma with unimaginable force. These cosmic monsters can accelerate particles to near light speeds, but even they struggle to explain the most extreme events. Another tantalizing possibility is decaying dark matter hypothetical particles left over from the Big Bang that, as they disintegrate, release bursts of energy capable of fueling these intergalactic cannonballs. Then there's the wild card, topological defects in spacetime itself, remnants of the universe's earliest moments, unraveling and releasing pent-up energy in violent bursts. The hunt for answers is a global effort. The Pierre Auger Observatory in Argentina, a sprawling array of detectors covering an area the size of Rhode Island, tracks the showers these cosmic rays create in Earth's atmosphere. Meanwhile, the telescope array in Utah scans the night sky for ultraviolet flashes signaling their arrival. Every detection is a breadcrumb, but the trail remains frustratingly faint. These particles are so rare that only a handful with truly extreme energies are spotted per century, and their paths are bent by magnetic fields, obscuring their origins like cosmic fingerprints smudged beyond recognition. What makes this enigma so electrifying isn't just the particles themselves, it's what they represent. Ultra-high-energy cosmic rays are messengers from the most violent corners of the universe, carrying secrets about physics operating at scales we can't replicate on Earth. They might hold clues about the nature of dark matter, the behavior of space-time under extreme conditions, or even entirely undiscovered forces. Until we solve their riddle, they'll keep raining down from the void, silent and relentless, reminding us that the universe still has accelerators far beyond our wildest imagination, and mysteries we've only begun to unravel. The universe has a secret bias, one so subtle it shapes everything we see, yet remains maddeningly out of reach. According to the laws of physics, the Big Bang should have produced matter and antimatter in perfect, symmetrical amounts. When these two meet, they annihilate in a flash of pure energy, leaving nothing behind. So why does anything exist at all? The fact that you're here watching this video means something tipped the scales. Matter won, but how? This is the Baryon asymmetry problem. And it's not just a curiosity, it's the reason stars, planets, and life itself didn't vanish into oblivion moments after creation. The search for answers leads us back to the universe's first microseconds. For matter to dominate, there must have been a tiny violation of symmetry in the early cosmos, a phenomenon known as CP violation. The C stands for charge flipping particles to antiparticles, and P for parity mirroring their spatial arrangement. Most physical processes treat matter and antimatter equally, like a perfectly balanced seesaw. But in rare cases, like certain particle decays observed in labs, the seesaw tilts slightly. The problem: the amount of CP violation we've measured is 1 billion times too small to explain the mountain of matter around us. It's as if nature left us a cryptic note, but the ink is so faint we can barely read it. One leading theory, called leptogenesis, suggests the imbalance might have started with neutrinos. These ghostly particles could have triggered a cascade of reactions in the early universe, favoring matter over antimatter through a process called the seesaw mechanism. Imagine a game of cosmic dominoes. If neutrinos decayed unevenly, they might have produced a slight excess of electrons and quarks, seeding the universe with the raw material for galaxies. Another idea points to primordial black holes, tiny, evaporating black holes from the Big Bang that could have selectively destroyed antimatter, leaving matter unscathed. Then there's the wild card, undiscovered particles. Theories like supersymmetry predict new particles that could interact in ways that amplify CP violation. Experiments like the Large Hadron Collider hunt for these exotic actors, but so far the stage remains empty. Meanwhile, observations of distant galaxies and the cosmic microwave background search for ancient imprints of the asymmetry, like fossils of the universe's first decisions. The stakes couldn't be higher. If we solve this puzzle, we won't just understand why we exist, we'll glimpse the hidden rules that shaped reality itself. Every atom in your body, every star in the sky, is a relic of that primordial imbalance. And until we crack it, the universe's greatest magic trick remains its best-kept secret. Imagine a particle so ghostly it could pass through a planet like light through a window, yet so pervasive it might outnumber atoms in the universe by 1 billion to 1. This is the action, a hypothetical particle born not from cosmic chaos, but from a mathematician's quest to tidy up the messy equations of quantum chromodynamics. In the late 1970s, physicists Roberto Pexi and Helen Quinn proposed this elegant solution to the strong CP problem, a nagging inconsistency in how the strong nuclear force treats matter versus antimatter. Their idea was simple. What if nature has a hidden symmetry, a cosmic seesaw that automatically balances these quantum scales? The action would be the physical manifestation of that balance, a particle so lightweight and weakly interacting it makes neutrinos look positively sociable. But here's the twist. Actions didn't just solve a theoretical puzzle. They also turned out to be a perfect candidate for dark matter. Unlike bulky WIMP or exotic primordial black holes, actions would be everywhere yet nearly invisible, drifting through space like an intangible fog. Their collective gravity could explain why galaxies rotate too fast, why light bends around invisible mass, and why the cosmos seems stuffed with matter we can't see. One elegant idea, two cosmic mysteries solved. It's the kind of theoretical two-for-one deal that makes physicists giddy. The hunt for actions is a masterclass in scientific ingenuity. Since they don't interact with light or ordinary matter, you can't just point a telescope and hope for a glimpse. Instead, researchers have built action haloscopes, ultra-sensitive devices that use powerful magnetic fields to coax actions into revealing themselves. The idea is that in the presence of a strong magnetic field, actions might occasionally convert into microwave photons, producing a faint signal at a frequency corresponding to the action's mass. Experiments like ADMCS at the University of Washington and CAP in South Korea have turned this concept into reality, tuning their detectors like cosmic radios searching for one elusive station among static. Yet the action's elusiveness is part of its charm. If they exist, their mass could be anywhere from a millionth of an electron volt to 1,000th, a range so vast it's like searching for a needle in a galaxy-sized haystack. Some theorists even propose action stars, exotic celestial objects made of densely packed actions that could be floating undetected in our galactic neighborhood. Others suggest actions might leave fingerprints in the polarization of starlight or the behavior of neutron stars. What makes this quest so thrilling isn't just the potential payoff, it's the way actions embody the best of theoretical physics, elegant, economical, and audaciously ambitious. Whether they are found or not, they remind us that the universe's deepest secrets might hide in the spaces between equations, waiting for the right mind to shine a light. And if that light finally catches a flicker in some underground lab, it won't just be a particle discovered, it'll be a triumph of human imagination over cosmic obscurity. The universe isn't silent, it thrums with a hidden symphony, a chorus of ripples cascading through the very fabric of space-time. These aren't the gravitational waves from individual collisions we've detected before, like the cataclysmic mergers of black holes or neutron stars that send sharp, transient chirps through our observatories. This is something far subtler, the gravitational wave background, a faint but persistent hum woven from countless cosmic collisions across the eons. Imagine standing in a crowded room where every conversation blends into a low, steady murmur, except here. The voices are the echoes of black holes dancing in the dark, neutron stars spiraling into oblivion, and who knows what else, all vibrating the cosmos like a drumhead struck in slow motion. Detecting this background isn't just about adding another layer to our cosmic soundtrack, it's about uncovering a lost history. Gravitational waves don't dim with distance the way light does. They're pristine messengers, carrying tales of events too ancient or too shrouded in dust for telescopes to see. Some of these waves might come from supermassive black holes merging in the universe's infancy, monsters that formed before the first stars flickered to life. Others could reveal entirely new classes of objects, cosmic strings, hypothetical defects in space-time left over from the Big Bang, or even the faint tremors of a multiverse bumping against our own. The gravitational wave background is a fossil record written in space-time itself, waiting for us to learn how to read it. The challenge is pulling this signal from the noise. Current detectors like LIGO and Virgo are exquisitely sensitive to sudden, high-frequency waves, but the background is a collective whisper, a sum of millions of overlapping events. To hear it, scientists are turning to pulsar timing arrays, networks of dead stars that spin with metronomic precision, beaming radio waves at Earth like cosmic lighthouses. As gravitational waves pass through space, they subtly stretch and compress the timing of these pulses, creating a pattern that, over years of observation, might reveal the background shape. Projects like NanoGrav in North America and the International Pulsar Timing Array are already teasing out hints, with recent data showing a tantalizing signal that could be the first murmur of this cosmic hum. But the real revolution lies ahead. Future space-based observatories like LISA, a trio of satellites set to launch in the next decade, will open a new frequency band, sensitive to waves from the slow-motion mergers of supermassive black holes. These collisions are the universe's base notes, vibrating space-time over years or even centuries, and their combined rumble could dominate the gravitational wave background. Mapping this hum would give us a census of black holes across cosmic time, revealing how they grew, merged, and shaped the galaxies around them. It might even solve one of astronomy's biggest mysteries: how some black holes became billions of times the sun's mass when the universe was barely a toddler. What makes this search so electrifying isn't just what we expect to find, it's what we can't yet imagine. The history of astronomy is littered with discoveries that came from listening to the universe in new ways, from radio telescopes revealing pulsars to gamma-ray detectors unmasking colliding neutron stars. The gravitational wave background could hold similar surprises, relics of physics beyond the standard model, evidence of extra dimensions, or even traces of the universe's birth before inflation. Every hum, every ripple is a thread in a story we're only beginning to unravel. And as our detectors grow more sensitive, we're not just hearing the cosmos, we're learning its language, one vibration at a time. Black holes have long been cosmic paradoxes devouring matter, light, and seemingly the very information that describes them. But what if these gravitational monsters aren't the ultimate shredders we thought they were? Cutting-edge breakthroughs in quantum gravity are painting a startling new picture. Black holes might not erase information at all. Instead, they could be meticulously preserving it, like celestial librarians encoding every swallowed star into the fabric of their event horizons. This revelation comes from a marriage of two radical ideas, holography and quantum entanglement, and it's turning our understanding of space-time inside out. At the heart of this revolution is the holographic principle, which suggests that all the information within a volume of space can be represented as a kind of quantum projection on its boundary. Think of it like a 3D movie encoded on a 2D surface, except here, the screen is the black hole's event horizon. When an object falls in, its information isn't lost. It's scrambled into a microscopic, two-dimensional pattern on the horizon surface. Later, as the black hole emits Hawking radiation, that information could be slowly leaked back out, woven into the radiation's quantum states. It's as if the black hole is performing the universe's most extreme data compression, squeezing three-dimensional reality into a two-dimensional archive. But how does this actually work? Enter quantum entanglement, the spooky action at a distance that Einstein famously resisted. Recent research suggests that the event horizon might be a tangle of quantum threads, each connecting particles inside the black hole to those radiating away outside. These threads act like cosmic glue, ensuring no information is ever truly severed, just transformed. Imagine a book burned to ash under classical physics. Its words are gone forever. But in this quantum picture, the ash still holds a hidden blueprint of the text, waiting to be decoded. Black holes, it seems, might operate on similar principles, with entanglement preserving the links between the interior and the escaping radiation. The implications are staggering. If true, this would resolve Stephen Hawking's infamous information paradox, which had threatened to topple quantum mechanics by suggesting black holes could permanently erase information. a violation of quantum theory's core tenet that information must always be conserved. Instead of a paradox, we'd have a profound unification, gravity and quantum mechanics working in harmony, with black holes as the ultimate quantum machines. It would mean that space-time itself might be emergent, stitched together by these entangled threads rather than being a fundamental backdrop, yet mysteries remain. How exactly does the information encoded on the horizon translate into the Hawking radiation we observe? Some theories propose a process called quantum error correction, where the chaos of the horizon scrambling is undone through intricate quantum protocols like a cosmic Sudoku puzzle where the numbers eventually align to reveal the original message. Others suggest that black holes might have soft hair, subtle quantum fields on their surfaces that store information in barely detectable imprints. The search for answers is driving some of the most audacious experiments in physics. Researchers are simulating black hole dynamics in quantum computers, testing how information might survive extreme gravitational environments. Others are studying analog black holes created in labs using sound waves or light, where event horizons form in controlled settings, and gravitational wave detectors like LIGO might one day spot subtle signatures in black hole mergers that reveal how information is preserved during these violent collisions. What's most thrilling isn't just the solution to a decades-old puzzle, it's the philosophical shift this represents. Black holes, once seen as the universe's ultimate endpoints, might instead be its most sophisticated storage devices. They're not destroying the story of the cosmos. They're rewriting it in a language we're only beginning to decipher. And as we peel back the layers of this quantum enigma, we're not just learning about black holes, we're uncovering the hidden rules that weave reality itself into existence. From dark matter's ghostly embrace to the mind-bending possibility of parallel realities colliding in hidden dimensions, these 50 cosmic revelations prove one undeniable truth: our universe operates on a scale of wonder that dwarfs even the wildest science fiction. What makes these mysteries so exhilarating isn't just their strangeness, but how they collectively expose the limits of human knowledge. Every time we think we've grasped the rules, the cosmos throws another curveball. Galaxies spinning too fast, particles vanishing into thin air, whispers of civilizations that might have built megastructures around distant stars. Each anomaly is a breadcrumb leading us deeper into the labyrinth of existence, reminding us that discovery isn't about finding answers, it's about learning to ask better questions. Consider how far we've come. A century ago, astronomers debated whether the Milky Way was the entire universe. Today, we're mapping the cosmic web's filaments, capturing black hole shadows, and decoding quantum fluctuations in the vacuum of space. Yet with every breakthrough, the universe unveils 10 new puzzles. The very fabric of reality behaves differently when we zoom into quantum scales versus when we observe galactic collisions. Dark energy accelerates the universe's expansion while dark matter sculpts its structure, yet both remain invisible to our detectors. Neutrinos change identities mid-flight like cosmic shape-shifters, and black holes might not be cosmic dead ends but holographic vaults preserving information in ways we're only beginning to fathom. What ties these mysteries together is their refusal to conform. They're not gaps in our knowledge, they're doorways. The Kuiper Cliff's abrupt edge hints at unseen planets or flawed models of solar system formation. The Hubble tension's conflicting expansion rates could reveal new physics or multiversal influences. Even failures to detect predicted particles like WIMP or magnetic monopoles force us to innovate, building bigger colliders, sharper telescopes, and more sensitive detectors. Science thrives on these tensions, these contradictions that keep us questioning. The most thrilling part, this golden age of discovery is just beginning. Upcoming marvels like the Vera Rubin Observatory's all-sky surveys, the Gravitational Wave Detector LISA launch, and quantum computers simulating black hole dynamics promise to peel back another layer of cosmic secrets. Perhaps we'll finally spot Planet 9 lurking in the outer solar system, catch an action converting in a magnetic field, or decode the gravitational wave background's primordial hum. Or maybe, just maybe, we'll stumble upon something entirely unexpected, a phenomenon that rewrites the textbooks overnight. That's the true gift of these enigmas. They keep the universe alive with possibility. Whether you're mesmerized by the eerie silence of the Fermi Paradox, chilled by the Boltzmann brain's existential riddle, or inspired by Dyson Sphere's engineering dreams, one thing's certain: the cosmos has a way of speaking to each of us differently. So tell us, which mystery makes your imagination catch fire? The comments are your launch pad. And if you're hungry for more deep dives into space's greatest puzzles, hit subscribe, because the next revelation is always just over the horizon. The universe isn't done surprising us yet, and neither are we.